Tonight, we are going to a planet that looks almost like Earth on paper and almost nothing like Earth in reality. Venus is nearly our size. It is made of similar rocky material. It formed beside us from the same young solar system, yet stand on its surface and the air would crush you under roughly 90 times Earth's sea level pressure, while temperatures hover near 467 degrees Celsius, hot enough to destroy most familiar machinery. Above that surface hangs an atmosphere dominated by carbon dioxide and clouds of sulfuric acid. This is not just a hot planet, it is the closest thing in our neighbourhood to a climate catastrophe written across an entire world. And that creates a disturbing question. Was Venus always this way, or did something happen to it? If it once had water, milder temperatures, perhaps even long-lived oceans, then the difference between Venus and Earth is not simply that one planet was born lucky and the other was born doomed. Somewhere in their histories, two similar worlds may have taken radically different paths. Before we go deeper, if you enjoy science that changes the way familiar worlds look, take a moment to like the video, subscribe, and comment with the planetary mystery you want us to investigate next. Because the real story of Venus is not just why it became hell, it is what that transformation can and cannot tell us about Earth. The first thing we need to destroy is a very tempting explanation. Venus is hotter because it is closer to the Sun. That is true, but it is nowhere near enough. Mercury is closer to the Sun than Venus, yet Venus has the hotter average surface. The reason is atmosphere. Venus is wrapped in an enormous blanket of carbon dioxide. Sunlight reaches the planet. The surface absorbs energy and tries to radiate heat back toward space, and the atmosphere makes that escape extraordinarily difficult. The result is a greenhouse effect pushed to an extreme that Earth has never experienced in human history. But even that description can mislead us if we imagine carbon dioxide as a simple switch that somebody turned too far. Venus is a system. Its temperature, atmosphere, water, rocks, clouds, sunlight and interior all interact. Once those pieces begin reinforcing one another, a planet can cross thresholds that are difficult to reverse. Water is central to that story. On Earth, water and rock participate in a long carbon cycle. Rain and chemical weathering help remove carbon dioxide from the air, while geology stores and returns carbon over immense spans of time. Earth's climate is not perfectly stable, but carbon does not simply remain trapped in the atmosphere forever. Venus appears to have ended up on the opposite side of that balance. Today it is extraordinarily dry. Measurements of its atmosphere, including the unusually high ratio of deuterium to ordinary hydrogen, have long suggested that Venus lost a large amount of water sometime in its past. The exact history remains uncertain. We do not know how much surface water Venus once had, how long it lasted, or whether the planet ever possessed oceans resembling Earth's. Models have produced very different histories, including scenarios in which early Venus remained temperate for long periods, and others in which it became hostile much earlier. That uncertainty matters, because the route into hell may not have been a single clean event. Still, the physical trap is clear enough to understand. As a wet, rocky planet warms, more liquid water evaporates. Water vapor is itself a powerful greenhouse gas. More vapor can trap more heat. More heat can drive more evaporation. Normally, a planet can still radiate enough energy to space to find a new balance. But under sufficiently intense heating, that balance can begin to fail. Climate scientists call the extreme endpoint a runaway greenhouse. Oceans evaporate. The atmosphere becomes thick with water vapor, and the planet approaches a state in which additional surface heating does not produce the usual increase in escaping thermal radiation fast enough to restore stability. Then the disaster moves upward. Once large amounts of water vapor reach high altitudes, ultraviolet sunlight can break water molecules apart. Hydrogen, being extremely light, can escape to space far more easily than oxygen. Over immense spans of time, a world can lose the raw material required to rebuild its oceans. The greenhouse is no longer merely warming water, it is helping remove water from the planet. And when the water disappears, Another protective pathway weakens. On a wet world, carbon dioxide can be drawn out of the atmosphere through reactions involving water and rock. On a dry world, with no Earth-like carbon cycle, volcanic carbon dioxide can accumulate instead of being efficiently returned to long-term surface reservoirs. Venus today contains an immense atmospheric inventory of carbon dioxide. Whether volcanism triggered a decisive ancient climate transition, amplified one already underway, or played different roles at different times is still being investigated. Some modelling has shown that episodes of massive volcanism could have helped push a previously temperate Venus toward its present state. That is plausible. It is not yet a solved historical reconstruction. This distinction is going to matter again and again. We know what Venus is now, with far greater confidence than we know exactly how it became that way. The surface tells us the ending. The atmosphere preserves fragments of the crime scene. The missing oceans, if oceans truly existed, are inferred from chemistry and climate models rather than photographed shorelines. The timing is blurred. The role of the interior is incomplete. New Venus missions are being built precisely because the missing pieces determine which history is actually true. And now we reach the question hidden inside the title. Could Earth be next? The frightening answer is not the simplistic one. Human-caused global warming is real. Adding carbon dioxide and other greenhouse gases to Earth's atmosphere traps additional heat and shifts the planet's energy balance. Water vapor then amplifies that initial warming as a feedback. Those are the same broad pieces of physics that make greenhouse climates possible elsewhere. But similarity of mechanism does not mean similarity of endpoint. Present-day Earth is not sitting one ordinary emissions increase away from turning into modern Venus. A true Venus-style runaway greenhouse requires conditions far beyond the warming projected from human greenhouse emissions alone under Earth's current solar environment. That does not make the comparison harmless. It makes it more useful. Venus shows us that planetary climate has regimes. A world can possess stabilizing feedbacks for immense periods and still have boundaries beyond which the old balance no longer works. Earth's immediate danger is not that our oceans are about to boil into a Venusian steam atmosphere. The danger is that much smaller changes are already powerful enough to reshape coastlines, rainfall, heat extremes, ecosystems, and the conditions under which human civilization developed. We do not need 467 degrees Celsius for climate physics to become consequential. So the real warning from Venus is subtler and in some ways more unsettling. Planets are not guaranteed to remain friendly simply because they once were. Habitability is something a world maintains through a moving balance of sunlight, atmosphere, water, geology, and time. Venus may be the place where that balance was lost. To understand whether it was lost slowly, suddenly, or perhaps much earlier than we once imagined, we have to go backward, past the sulfuric acid clouds, past the crushing carbon dioxide, past the furnace surface, and reconstruct the Venus that no spacecraft ever saw. If we could strip away the atmosphere and look beneath the clouds, Venus would not appear completely alien. It is a rocky planet with mountains, valleys, enormous volcanic plains, impact craters, fractured terrain, and vast regions shaped by forces coming from deep inside the world. The surface is hostile beyond anything on Earth, but its geology keeps pointing toward a much more important question. How long has Venus looked like this? That question is harder than it sounds because Venus has erased much of its own history. On Earth, geologists can examine rocks that are billions of years old. They can trace ancient shorelines, read minerals formed in water, study sediment deposited in vanished oceans, and reconstruct climates that disappeared long before humans existed. Venus gives us almost none of that access. Its dense clouds hide the surface from ordinary visible light observation, and the spacecraft that have actually landed there survived only briefly before the heat and pressure overwhelmed them. So researchers have had to reconstruct Venus indirectly. Radar became one of the most powerful tools. Between 1990 and 1994, NASA's Magellan spacecraft mapped almost the entire Venusian surface, using radar capable of penetrating the planet's clouds. What emerged was a world covered by volcanic structures on an almost overwhelming scale. There are huge lava plains, immense shield volcanoes, strange circular features called coronae, and regions where the crust appears to have been stretched, fractured, compressed, or broken repeatedly. Venus does not look geologically dead. And that matters because volcanism may have been one of the forces that transformed its atmosphere. A volcano does more than move molten rock. It can also move enormous quantities of gas from a planet's interior into its atmosphere. On Earth, volcanic eruptions release water vapor, carbon dioxide, sulfur compounds, and other gases. Earth can process much of that carbon through oceans, weathering, biological activity, sedimentation, and plate tectonics. Venus does not appear to operate that way today. It has no Earth-like global system of moving tectonic plates. Instead, heat from the interior may escape through a very different geological regime. Exactly how that regime has changed through time remains one of the central mysteries of the planet. Imagine a younger Venus with significantly more water than it has today. If liquid water remained on the surface, then some atmospheric carbon dioxide could potentially have interacted with rocks and water. Under the right conditions, carbon might have been transferred out of the atmosphere and stored in minerals, as happens through parts of Earth's long-term carbon cycle. But begin removing the water, and that machinery starts breaking down. The hotter the planet becomes, the more water moves into the atmosphere. The more water it loses to space, the less remains available at the surface. Weathering changes. Carbon storage changes. The atmosphere becomes increasingly dominated by gases that can retain heat. Now add volcanism. Carbon dioxide released from the interior can build up. Sulfur compounds alter atmospheric chemistry and cloud formation. Surface temperatures remain high enough to prevent liquid water from returning. Instead of restoring the old climate state, each part of the planet begins reinforcing the new one. That is the possibility that makes Venus so fascinating. Its catastrophe may have become self-amplifying, but there is a problem with telling this story too confidently. We do not yet know whether Venus ever had the kind of ocean-covered surface we instinctively imagine. Some climate simulations have suggested that ancient Venus could have maintained temperate surface conditions for surprisingly long periods if it began with enough water, and if its atmospheric and rotational conditions allowed reflective clouds to limit solar heating. That would give Venus an extraordinary history. For perhaps hundreds of millions or even billions of years, Earth might not have been the only relatively mild, rocky world near the Sun. Venus could have occupied a completely different climate state before crossing into the one we see now. Yet other models challenge that picture. A young Venus may have been so hot that water vapor never condensed into stable oceans in the first place. The early Sun was fainter than it is today, but newly formed rocky planets also retained tremendous internal heat. Their surfaces could remain molten or extremely hot, while thick steam atmospheres trapped energy. Under some scenarios, Venus may never have passed through a long Earth-like phase at all. Its water could have remained largely atmospheric, where sunlight gradually broke it apart and hydrogen escaped into space before permanent oceans had much chance to form. Those two histories are radically different. In one, Venus was a habitable-looking world that eventually collapsed. In the other, it was on the road toward its present state almost from the beginning. And from orbit, billions of years later, both histories can leave us staring at the same furnace. This is why certain regions on Venus have attracted so much attention. They are called tesserae. Tessera terrain consists of highly deformed highlands crossed by complicated ridges and fractures. These regions appear older than many surrounding volcanic plains, meaning they may preserve fragments of an earlier Venus before much of the modern surface was created. If there are ancient rocks capable of revealing whether liquid water once interacted with the crust, tesserae are among the places scientists would most like to understand. Their mineral composition could be decisive. Some types of rock form or are altered under conditions involving water. Detecting those signatures would not instantly prove that Venus once possessed deep global oceans, but it could provide evidence that surface water played a meaningful role in its geological past. And that brings us to another strange feature of Venus. Its surface seems surprisingly young. When planetary scientists estimate the ages of surfaces, they often count impact craters. Older terrain generally has had more time to accumulate impacts. Venus has relatively few craters, compared with what we might expect if its visible surface had remained unchanged for most of solar system history. That suggests extensive resurfacing. But resurfacing does not necessarily mean that one apocalyptic event repaved the entire planet overnight. For years, a dramatic hypothesis proposed that Venus experienced something close to a global volcanic catastrophe hundreds of millions of years ago, covering vast areas in fresh lava and effectively resetting much of the crater record. The reality may be more complicated. Different parts of Venus could have been resurfaced at different times. Volcanic activity may have continued over long intervals. Some regions may be ancient, while others are geologically young. And evidence increasingly points toward a Venus that may still be volcanically active now. That changes the planet psychologically as much as scientifically. Venus is not necessarily the fossilized remains of one catastrophe that ended long ago. The interior may still be shaping the surface. The atmosphere may still be interacting with volcanic gases. The planet may still be evolving. Which means that when we ask why Venus became hell, we are trying to reconstruct a transformation that may never have truly stopped. Somewhere in that history, water, rock, sunlight, atmospheric escape, volcanism and carbon became locked into a configuration from which modern Venus could no longer easily return. But there is one clue that takes us even deeper. High above the volcanic plains, almost all of the original water is gone. The small amount that remains carries an isotopic fingerprint. And that fingerprint may tell us just how enormous the loss really was. The clue is hidden inside something almost too small to imagine. Hydrogen. More precisely, two different versions of hydrogen. Ordinary hydrogen has one proton in its nucleus. Deuterium is heavier because it carries a proton and a neutron. Chemically, both can become part of water, but physically they do not behave in exactly the same way. That tiny difference in mass becomes extraordinarily important when an atmosphere starts leaking into space. Venus has an unusually high ratio of deuterium to ordinary hydrogen compared with Earth. And that is a If Venus once contained much more water, ultraviolet radiation from the Sun could split water molecules high in the atmosphere. Oxygen and hydrogen would separate. The lighter hydrogen atoms could then escape more easily into space, while the heavier deuterium would be somewhat more difficult to remove. Over time, preferentially losing ordinary hydrogen would leave the surviving water enriched in deuterium. It is the planetary equivalent of discovering that most of something has vanished because the residue left behind has been chemically sorted. But this clue comes with an important limitation. The deuterium ratio tells us that Venus experienced substantial water loss. It does not provide a simple photograph of how much ocean once existed on the surface. To turn an isotope measurement into an ancient ocean depth, scientists must make assumptions about the planet's original composition, atmospheric chemistry, escape rates, geological recycling, and how those processes changed over billions of years. Change the assumptions, and the reconstructed past changes too. So when we hear that ancient Venus may once have possessed an ocean, we should not picture a coastline with the confidence we might picture an ancient sea on Earth. The evidence is suggestive, potentially powerful, but incomplete. What is far harder to dispute is that Venus lost water, and once we follow that water upward, another difference between Venus and Earth begins to appear. Earth has a magnetic field generated by motion inside its metallic core. That field creates a magnetosphere extending far beyond the atmosphere, interacting with charged particles coming from the Sun. Venus has no comparable internally generated global magnetic field today. It might be tempting to stop there and say that this is why Venus lost its water. But planetary atmospheres are rarely that simple. A magnetic field can affect how the solar wind interacts with an atmosphere. Yet having no global magnetic field does not automatically mean an atmosphere will simply be blown away. Venus still possesses an enormous atmosphere, despite its lack of an Earth-like magnetosphere. In fact, the solar wind interacting with the Venusian ionosphere creates an induced magnetic environment of its own. Atmospheric escape happens through several pathways. Some particles can gain enough thermal energy to escape. Others can be accelerated by electrical fields, chemical reactions, or interactions with the solar wind. Ultraviolet and extreme ultraviolet radiation can heat the upper atmosphere and help drive escape. The importance of each mechanism changes depending on the planet, the molecule, the altitude, and the activity of the star. And the young sun was not the sun we see now. Early in solar system history, it emitted less total visible light, but it was much more active at high energies. Strong ultraviolet and X-ray radiation would have attacked the upper atmospheres of the young terrestrial planets. Solar activity and the solar wind could be far more intense than they are today. For a planet already hot enough to place large amounts of water vapor high in its atmosphere, that mattered enormously. Earth had another advantage: a cold trap. In our present atmosphere, temperatures near the tropopause help limit how much water vapor reaches the upper atmosphere. Most water stays lower down, where it can condense and return to the surface as rain or snow. That greatly slows the destruction and loss of water. But warm a planet enough, and the cold trap can weaken. More water vapor reaches higher altitudes, more molecules become exposed to ultraviolet radiation, more hydrogen becomes available to escape. This is called a moist greenhouse state. It is not necessarily the same thing as a full runaway greenhouse. That distinction matters. A planet can begin losing water efficiently before its oceans have completely evaporated and before surface temperatures resemble modern Venus. In other words, there may be multiple doors on the road toward permanent desiccation. Venus may have passed through some of them. Once enough water disappeared, returning to a wetter state would have become increasingly difficult. Hydrogen escaping to space is not simply moved somewhere else on the planet. Much of it is gone. The world has lost part of the chemical inventory needed to make water. Oxygen creates another mystery. If enormous quantities of water were destroyed, where did all the oxygen go? Some oxygen could also escape to space. Some could react chemically with the surface and become incorporated into rocks. The Venusian crust may therefore preserve part of the answer, locked into oxidation states that future measurements could help reveal. This is one reason studying the surface composition matters so much. The atmosphere tells us what remains above. The rocks may tell us what disappeared into the ground. Now place Earth beside Venus. The similarities are almost uncomfortable. Earth's diameter is only modestly larger, its mass is only modestly greater. Both planets are made primarily of rock and metal. Both likely obtained volatile materials during formation and early bombardment. Both experienced volcanism. Both received energy from the young sun. Yet one retained vast surface oceans. The other did not. Distance from the sun was undoubtedly important. But distance is only the beginning of the explanation. Venus receives substantially more solar energy than Earth. That extra energy changes whether water can condense, how much water vapor reaches the upper atmosphere, how strongly greenhouse feedbacks operate, and how close the planet sits to climate thresholds. The planetary history may amplify small initial differences. Suppose two worlds begin only moderately different. One cools enough for stable oceans to form. Liquid water begins weathering rocks. Carbon dioxide is gradually transferred into minerals and sediments. Surface temperatures remain within a range that keeps most water low in the atmosphere. The planet retains its oceans. Now take the other world. It receives more sunlight. Its surface remains warmer. More water enters the atmosphere. Its upper atmosphere becomes wetter. Hydrogen escapes more rapidly. Surface water declines. Weathering and long-term carbon storage become less effective. Volcanism continues supplying carbon dioxide. The greenhouse strengthens. The difference between the two planets grows, and then grows again. This is what feedback can do. It can turn a relatively modest initial difference into two completely different planetary outcomes. But there is still another complication. Venus rotates incredibly slowly. One Venusian rotation relative to the distant stars takes about 243 Earth days, and it spins in the opposite direction from most planets. Its solar day, from one noon to the next, lasts about 117 Earth days. That strange rotation changes atmospheric circulation and cloud behavior. And climate models have produced a surprising possibility. A slowly rotating ancient Venus with liquid water might have developed enormous reflective cloud systems on its day side. Those clouds could have bounced a significant amount of incoming sunlight back to space, cooling the planet and allowing temperate conditions under levels of solar radiation that might otherwise seem impossible. That means proximity to the Sun alone may not have doomed Venus immediately. Clouds might have delayed the catastrophe, perhaps for a very long time. If that scenario is correct, then Venus becomes more disturbing, not less. Because it would mean the planet may once have balanced near habitability despite receiving far more sunlight than Earth. And eventually, something broke that balance. Maybe increasing solar brightness was enough. Maybe changes in volcanism mattered. Maybe atmospheric composition shifted. Maybe several processes converged. Or perhaps the entire temperate Venus scenario is wrong and the planet never had stable oceans at all. There is a way to begin separating these possibilities. We need to know what Venus is made of, not just in its atmosphere, but in its oldest rocks. And several upcoming investigations are designed to do exactly that. Because the next major breakthrough may not come from another climate model, it may come from descending directly through the clouds. To understand why a descent through Venus matters, we need to stop thinking of its atmosphere as nothing more than an obstacle. It is an archive. Every layer contains information about what the planet has lost, what its interior has released, and how its climate evolved. The gases surrounding Venus today are the surviving pieces of processes that may have begun more than 4 billion years ago. A probe falling through those clouds would therefore be doing something much more ambitious than measuring weather. It would be reading history. The first part of the descent would begin in a region that, strangely enough, is far less hostile than the surface below. High in the Venusian atmosphere, temperatures and pressures pass through ranges that are surprisingly familiar by planetary standards. This is one reason the cloud layers have attracted so much scientific attention. But the clouds themselves are anything but Earth-like. They are dominated by droplets containing sulfuric acid. Below and around them, atmospheric circulation races around the planet far faster than the solid world rotates beneath it. Venus takes about 243 Earth days to rotate once relative to the distant stars, yet its upper atmosphere can circle the planet in only a few Earth days. This phenomenon is called superrotation. The atmosphere is effectively outrunning the planet. Exactly how Venus maintains such extreme atmospheric motion remains an active area of research. Waves, thermal tides, momentum transfer, and interactions between different atmospheric layers all contribute. But for our story, the crucial point is that Venus is not a static greenhouse wrapped around a dead rock. It is a dynamic climate machine. As a descending probe moves downward, pressure rises. Temperature rises. The chemistry changes. And gradually, the atmosphere begins revealing clues that telescopes and orbiters cannot measure with the same precision. Among the most valuable are the noble gases: helium, neon, argon, krypton, xenon. They sound almost irrelevant to a climate catastrophe because most noble gases do not participate strongly in ordinary chemical reactions. That is precisely why scientists care about them. Reactive molecules can be created, destroyed, locked into rocks, dissolved in liquids, or transformed through chemistry. Noble gases are harder to alter chemically. Their abundances and isotopic ratios can therefore preserve information about the materials from which a planet formed and the atmospheric losses it later experienced. Think of them as fingerprints that are difficult for geological history to erase. If Venus suffered enormous atmospheric escape early in its life, some isotopic ratios should carry evidence of that fractionation. If giant impacts removed parts of the primordial atmosphere, other signatures may survive. If volcanic outgassing rebuilt the atmosphere later, measurements of gases released from the interior could help reveal that history. This is where one measurement can become much larger than itself. Consider xenon. On Earth and Mars, xenon isotopes have provided clues about ancient atmospheric evolution. Venus remains poorly characterized by comparison. Precise measurements could help determine whether the planet experienced major early atmospheric loss and whether its present atmosphere is mostly ancient, mostly rebuilt, or some complicated combination of both. Then there is argon. Different argon isotopes can trace different processes. Some were incorporated during planetary formation. Others are produced by radioactive decay inside rocks. Their relative abundance can reveal something about how much material has been released from the interior over geological time. That connects the atmosphere directly to volcanism. And suddenly we are no longer asking only whether Venus lost water. We are asking when its interior released gases, how efficiently those gases escaped, whether the surface exchanged material with the atmosphere, and whether the planet experienced one major transition or several. A good atmospheric profile could begin separating those histories. Carbon itself carries clues. Different isotopes of carbon may tell us about atmospheric escape and interactions with rocks. Oxygen isotopes can help constrain exchange between the atmosphere and surface materials. Sulfur chemistry can reveal volcanic and photochemical processes. No single measurement solves Venus. The power comes from combining them. Imagine that the deuterium to hydrogen ratio suggests massive water loss. Noble gases reveal strong early escape. Surface minerals indicate little evidence of long-term interaction with liquid water. Together, those clues might favor a Venus that became dry very early. Now imagine a different result. Suppose ancient highland rocks show chemical alteration consistent with substantial water. Suppose atmospheric isotopes indicate that major water loss occurred later than the earliest phases of planetary formation. Suppose geological evidence points toward long periods of crustal stability followed by intense volcanic disruption. That combination would strengthen the case for a Venus that remained temperate for a significant fraction of its history before changing dramatically. The same planet, two completely different biographies. That is why landing on Venus remains so difficult and so valuable. The Soviet Venera program proved that the surface could be reached. Several Venera spacecraft survived long enough to return measurements, and some transmitted the first images from the surface of another planet. Those images remain astonishing. There are no oceans, no vegetation, no blue horizon. Instead, slabs of rock sit beneath a thick yellow-orange atmosphere, illuminated through layers of cloud above. The landscape appears almost ordinary until we remember the conditions surrounding the camera. The pressure is comparable to what we would experience deep beneath Earth's oceans. The temperature is high enough to melt lead. Electronics, seals, batteries, sensors, and structural components all face relentless thermal stress. Building a spacecraft that can function there is less like designing an ordinary planetary lander, and more like building a machine for the inside of an industrial furnace under crushing pressure. Yet even a short survival time can transform our understanding. A descent probe can sample the atmosphere continuously while falling. A lander can measure elemental composition. Radar can reveal surface structure from orbit. Infrared observations can search for thermal variations. Repeated radar mapping can look for geological changes. And each method attacks a different part of the mystery. One of the most exciting clues has already come from comparing radar observations taken years apart. Scientists examining Magellan data identified changes at a volcanic vent in the region called Mart Mons. The vent appeared to change shape between two radar observations made months apart in 1991. Modeling suggested that the difference could be consistent with volcanic activity occurring during the mission. That does not mean Venus is covered in eruptions every day, but it strengthens the case that volcanism is not merely ancient history. Another line of evidence comes from atmospheric sulfur dioxide. Its abundance above the clouds has varied over time. Because sulfur dioxide can be removed from the upper atmosphere relatively quickly by chemical processes, changes in concentration have raised the possibility that fresh volcanic material may sometimes be resupplying it from below. There are alternative explanations involving atmospheric circulation, so again, caution matters. But the pieces keep pointing in the same direction. Venus may still be releasing heat. It may still be releasing gases. Its geological story may still be active. And if volcanism remains active today, then understanding its past becomes even more important. Because carbon dioxide in Venus's atmosphere did not appear from nowhere, a vast amount of carbon now sits overhead. On Earth, much of our carbon is stored elsewhere. In oceans, carbonate rocks, sediments, living systems, soils, and the mantle. If we somehow released Earth's long-term carbon reservoirs into the atmosphere, while simultaneously removing the oceans and shutting down the processes that recycle carbon back into rock, our atmosphere would become radically different. Not identical to Venus, but the comparison reveals something essential. The difference between two planets cannot be judged only by what is in their atmospheres today. We have to ask where the same materials are stored. Earth stores enormous amounts of carbon in rock. Venus stores an enormous amount in air. Earth keeps most of its water on the surface. Venus has lost almost all of its accessible water. Those reservoirs determine climate, and reservoirs can move. That brings us closer to the part of the Venus story that matters most for Earth. Because Earth's climate is stable only in a relative sense, it has changed dramatically before ice has expanded toward the tropics. Carbon dioxide has risen and fallen. Mass extinctions have followed rapid environmental disruptions. Yet after billions of years, Earth still has oceans. So the next question is not whether Earth can become warmer. We already know it can. The harder question is what has prevented Earth from becoming Venus for more than 4 billion years, and how long those protections can actually last. The answer begins with something Earth does so quietly that it is easy to miss. It moves carbon, not just through the atmosphere, but through oceans, soils, living systems, sediments, crust, and mantle. Carbon is constantly being transferred from one reservoir to another. Some of those exchanges happen in days, others take millions of years. And over geological time, that movement has helped keep Earth from locking most of its carbon into the atmosphere. One of the most important parts of this system begins with rain. Carbon dioxide dissolves into water and helps form a weak acid. As rainwater passes through soils and across exposed rock, it participates in chemical weathering. Certain minerals react. Dissolved material is transported toward rivers and oceans, and carbon can eventually become incorporated into carbonate sediments. Those sediments may remain stored for immense periods. Some are carried into Earth's interior through plate tectonics. Some carbon later returns through volcanic activity. The result is not a perfect thermostat, but something remarkably powerful, a long-term geochemical feedback linking temperature, rainfall, rock, oceans, and atmospheric carbon dioxide. Warm conditions can often accelerate weathering. More weathering can remove more carbon dioxide. Less atmospheric carbon dioxide reduces greenhouse warming. Cooling can slow the process. That feedback operates slowly, far too slowly to regulate climate on human timescales, but across millions of years it has helped Earth remain within a broad range where liquid water could survive. Venus today cannot run the same system. There is no global ocean carrying dissolved material across its surface. There is no rain reaching the ground. There is no known Earth-style network of moving tectonic plates continuously recycling crust. And with surface temperatures near 467 degrees Celsius, the chemistry of the surface operates under radically different conditions. This does not mean Earth's plate tectonics alone saved the planet. That explanation is too simple. Scientists still debate exactly how essential plate tectonics is for long-term habitability. Other forms of crustal recycling may also exchange material between a planet's surface and interior. Even Earth's own tectonic history is complicated, especially during its earliest billion years. But our planet clearly possesses something Venus lacks today: a functioning ocean rock atmosphere system capable of moving enormous quantities of carbon away from the air. Water makes that possible. And here the story becomes circular. Water helps regulate carbon dioxide. Carbon dioxide helps regulate temperature. Temperature determines whether water remains liquid. Lose enough water, and carbon regulation can weaken. Allow enough carbon dioxide to accumulate, and temperature rises further. Planetary stability is not the product of a single protective mechanism. It emerges from relationships. That is one reason Earth's oceans are far more important than simply being places where life exists. They are massive climate reservoirs. Water absorbs enormous quantities of heat. Ocean circulation redistributes that heat around the globe. Carbon dioxide dissolves into seawater. Chemical reactions transform it into different forms of dissolved carbon. Marine organisms, where present, can further alter how carbon moves into sediments. Remove the oceans, and Earth would not merely become a dry version of itself. Its entire climate engine would change. Venus shows what happens when that engine operates under a completely different set of boundary conditions. But there is another major difference between the two worlds. Clouds. Clouds sound simple until we try to predict what they do to an entire planet. Some clouds reflect sunlight and cool the surface. Others trap outgoing infrared radiation and warm it. Their net effect depends on altitude, thickness, composition, particle size, location, and the underlying atmosphere. On Earth, clouds remain one of the most important sources of uncertainty in determining exactly how much warming will follow a given increase in greenhouse gases. On Venus, clouds behave differently again. Its global sulfuric acid cloud deck reflects a huge fraction of incoming sunlight. Venus is one of the brightest planets in our sky, partly because those clouds are extremely reflective. That creates a strange paradox. Venus absorbs less solar energy than we might assume from simply looking at its distance from the Sun. Yet its surface remains extraordinarily hot. The reason is that the atmosphere is so thick and infrared opaque that the heat retained below overwhelms the cooling effect of the reflective clouds. This is an important lesson. A planet's climate cannot be understood by looking at only one number. Not distance from its star, not atmospheric carbon dioxide alone, not cloud reflectivity, not even surface temperature. The entire vertical structure matters. Where sunlight is absorbed matters. Where infrared radiation escapes matters. Atmospheric pressure matters. Collision between molecules matters. Cloud formation matters. Circulation matters. And all of these variables can change as the planet changes. This is where the phrase runaway greenhouse often becomes distorted in popular discussions. A greenhouse effect and a runaway greenhouse are not the same thing. Earth has a natural greenhouse effect right now. Without greenhouse gases, our average surface would be dramatically colder. Human activity is strengthening that greenhouse effect by increasing concentrations of carbon dioxide, methane, and other heat-trapping gases. That warming is measurable, physically understood, and consequential. But it does not follow that every additional degree of warming pushes Earth automatically into a Venus-like runaway. A true runaway greenhouse is a much more extreme physical regime. As surface temperature climbs, more water evaporates. Water vapor increases atmospheric opacity. Eventually, under sufficiently intense conditions, the planet can approach a limit on how much thermal radiation a water-rich atmosphere can effectively send to space. If absorbed solar energy exceeds what the planet can radiate away, equilibrium becomes impossible while surface oceans remain. Heating continues, more ocean evaporates. The greenhouse intensifies. That is the runaway. Present-day anthropogenic warming is not expected to trigger that full Venus-style process. This point deserves to be stated clearly because exaggerating the Venus comparison makes the real danger harder to understand, not easier. Burning fossil fuels cannot simply transform modern Earth into modern Venus. Even releasing all conventional fossil carbon would not give Earth a 90-bar carbon dioxide atmosphere or raise the global surface toward hundreds of degrees Celsius. The physics does not support that scenario. But stopping there would create the opposite mistake. Because a planet does not need to become Venus to become profoundly hostile to the civilization living on it. Earth's climate system contains other thresholds. Ice sheets can retreat. Ocean circulation can reorganize. Permafrost can thaw. Forests can shift or die back. Marine ecosystems can lose oxygen. Sea level can continue rising long after atmospheric temperatures stabilize. Regional heat can cross limits that make ordinary human activity dangerous. None of these requires boiling the oceans, and none becomes unimportant simply because Venus is worse. The useful comparison is therefore not human emissions equal Venus. They do not. The useful comparison is this. Climate depends on physical feedbacks, and feedbacks can amplify forcing. Earth has already demonstrated this throughout its own geological history. Consider the transition out of ice ages. A small initial change in Earth's orbital geometry alters how sunlight is distributed. Ice begins responding. As reflective ice retreats, darker surfaces absorb more sunlight. Carbon dioxide and methane concentrations change. Warming spreads. The final temperature change becomes much larger than the original orbital trigger alone would produce. That is feedback in action. The same principle operates in the opposite direction when ice expands. Earth's climate is responsive because its components interact. Venus represents an extreme example of where interacting components can ultimately lead. But Earth has something else Venus may never have possessed in the same way. A biosphere that has been modifying the planet for billions of years. Life has changed atmospheric chemistry, soil formation, weathering, ocean chemistry, and carbon burial. Photosynthetic organisms transformed the atmosphere by producing oxygen. Marine ecosystems moved carbon through food webs and sediments. Land plants later altered weathering and the exchange of water between continents and atmosphere. Life did not simply adapt to Earth. Life became part of Earth's climate system. Yet even that is not a magical shield. Life has survived enormous climate disruptions because life is adaptable as a planetary phenomenon. Individual species are not. Most species that have ever existed are extinct. The biosphere can persist through changes that devastate ecosystems and reorganize the planet for millions of years. That distinction matters when we ask whether Earth itself is in danger. The rock will survive us. The oceans will not suddenly vanish next century. The planet will continue orbiting the sun. The meaningful question is whether the climate conditions supporting modern coastlines, agriculture, infrastructure, ecosystems, and billions of people remain within the range in which those systems developed. Venus does not tell us that Earth is about to become hell. It tells us something deeper. Habitability is not a permanent property stamped onto a planet at birth. It is a state, and every state exists because certain physical relationships continue to hold. To understand how secure ours really is, we need to look not at Venus next, but backward into Earth's own past. Because our planet has already come much closer to climate catastrophe than the familiar blue world around us suggests, Earth's past is not the story of a planet sitting peacefully inside a perfect climate zone. It is the story of a planet surviving repeated shocks. There were times when ice reached astonishingly low latitudes, times when the polar regions supported forests, times when enormous volcanic provinces released gases across continents. Times when oceans lost oxygen, ecosystems collapsed, and most species alive disappeared from the fossil record. Earth remained habitable, but habitable can hide an enormous amount of violence. One of the clearest examples comes from about 252 million years ago, at the end of the Permian period. Something went catastrophically wrong. Volcanism on an almost unimaginable scale erupted across what is now Siberia. The Siberian traps were not a single volcano exploding once. They represented vast episodes of magma reaching or approaching the surface over an extended interval, producing enormous lava flows and releasing gases from Earth's interior. Carbon dioxide entered the atmosphere. Temperatures rose. The oceans warmed. Their chemistry changed. Oxygen declined in large regions of the sea, and the biological consequences were devastating. The end Permian mass extinction became the most severe known extinction event of the Phanerozoic eon. Marine ecosystems were hit especially hard, and terrestrial ecosystems were transformed as well. Earth did not become Venus. But for the organisms living through it, that distinction would have offered little comfort. This is where planetary language can mislead us. When scientists say Earth remained habitable, they mean that some environments continued allowing life to exist. They do not mean the climate remained comfortable, stable, or favorable to the species that had previously dominated the world. Life can survive planetary conditions that civilization cannot. A bacterium living underground and a global agricultural society do not have the same definition of habitability. That difference becomes essential when we bring Venus back into the comparison. Venus is the extreme endpoint. Earth's geological record shows the enormous territory that exists before that endpoint. You can destabilize climate without boiling an ocean. You can trigger mass extinction without producing a runaway greenhouse. You can radically reorganize coastlines, rainfall, ecosystems, and food webs, while the planet remains unmistakably Earth. And the fossil record contains more than one warning. Roughly 56 million years ago, during an event known as the Paleocene-Eocene thermal maximum, large quantities of carbon entered the ocean atmosphere system over a geologically short interval. Global temperatures rose. The oceans became more acidic. Species distributions shifted. Deep-sea ecosystems suffered major changes. The world eventually recovered, but that recovery unfolded over timescales vastly longer than a human lifetime. This is another crucial difference between geological resilience and human experience. Earth has time. Civilizations do not have unlimited time. A climate disruption can eventually be absorbed by weathering, ocean chemistry, sedimentation, biological change, and geological cycling. But if those processes require tens of thousands or hundreds of thousands of years, they provide no practical rescue for societies facing changes over decades and centuries. The planet can recover after we are gone. That is not the same thing as protecting us. Now go farther back, and Earth reveals the opposite climate extreme. There were intervals hundreds of millions of years ago when ice may have covered much of the planet. These episodes are commonly associated with the idea of snowball Earth. The exact extent of global ice cover remains a subject of scientific investigation, but geological evidence indicates extraordinary glaciations during the Neo-Proterozoic era. Imagine what such a world does to sunlight. Ice is bright. It reflects a large fraction of incoming solar radiation back into space. If ice expands, more sunlight is reflected. That produces cooling. Cooling allows more ice to expand. More ice creates more reflection. This is the ice albedo feedback. It is the mirror image of the kind of amplification we have been discussing on Venus. Feedback does not care whether the initial direction is hot or cold. It amplifies change when the physical relationships favor amplification. So how could an extensively frozen Earth escape? One proposed mechanism, again, leads underground. Volcanoes continue releasing carbon dioxide even when surface weathering is severely reduced by ice. If carbon dioxide enters the atmosphere faster than geological processes remove it, concentrations can gradually rise. The greenhouse strengthens. Eventually, enough warming may accumulate to begin melting ice. Once dark ocean or land is exposed, it absorbs more sunlight than ice. Melting accelerates. The climate shifts rapidly in the opposite direction. A planet can therefore contain both stabilizing and destabilizing feedbacks at the same time. Which one dominates depends on the state of the system. This is the deeper lesson Venus gives us. Climate does not respond along one smooth, perfectly predictable line. The same physical planet can behave differently in different regimes. Ice coverage changes reflectivity. Water vapor changes greenhouse strength. Clouds respond to temperature and circulation. Vegetation changes land reflectivity and water exchange. Oceans absorb heat and carbon. Permafrost stores carbon that can be released when it thaws. The system is interconnected. That does not mean every feedback becomes runaway. Most do not. Negative feedbacks oppose changes. Positive feedbacks amplify them. And climate science is largely about understanding their combined strength, timescale, and limits. The word tipping point enters here. It is often used too loosely. A climate tipping element is not necessarily a button that suddenly destroys the entire planet. It refers to a component of the Earth system that may undergo a large or potentially self-sustaining change after enough forcing is applied. An ice sheet can lose stability. A forest system can reorganize. An ocean circulation pattern can weaken dramatically. Permafrost thaw can release additional greenhouse gases. These processes differ enormously in probability, speed, reversibility, and global impact. They should not be collapsed into one cinematic doomsday scenario, but neither should they be ignored simply because none would turn Earth into Venus. Consider the great ice sheets. The Greenland and Antarctic ice sheets contain enough frozen water to reshape global coastlines dramatically if large portions are lost over long timescales. They do not need to disappear next year to matter. Once an ice sheet enters sustained retreat, some parts of that process can continue for centuries or longer, because ice responds slowly to a warmer climate. The atmosphere might stabilize before the ice does. The ocean might keep rising after the initial forcing stops increasing. This delayed response is one of the most difficult features of planetary systems to intuit. Cause and consequence do not always arrive together. Carbon dioxide released today can influence climate for a very long time. Heat accumulated in oceans can remain there long after a single hot year ends. Ice sheets integrate warming across generations. The climate system has memory. Venus has memory too. Its atmosphere remembers lost water through isotopes. Its surface remembers volcanism through lava plains and fractured terrain. Its rocks may preserve chemical evidence of climates that disappeared billions of years ago. Planetary history is written into reservoirs that respond at different speeds, and Earth is writing new history now. Atmospheric carbon dioxide has increased because humans are transferring carbon from geological reservoirs into the air on a timescale far faster than the natural processes that originally buried much of it. That does not reproduce the full ancient history of Venus. It does something much more immediate. It changes Earth's energy balance. And because the climate system contains feedbacks and long-lived components, the eventual consequences are not limited to the moment when the carbon enters the atmosphere. But there is a dangerous conceptual trap here. If Venus teaches us that feedbacks matter, we might assume that enough human warming must eventually trigger a hidden switch and send Earth irreversibly toward 467 degrees Celsius. That is not what current physics says. The sun itself provides the missing piece, because even if humanity disappeared tomorrow, Earth would not remain in its present climate forever. We star is slowly changing. As the sun ages on the main sequence, it becomes brighter. Over sufficiently long timescales, Earth will receive more solar energy than it does today. That increase is tiny on human timescales. Across hundreds of millions of years, it becomes profound. Eventually, a future Earth may encounter the very problem Venus already represents. More sunlight, more evaporation, more water vapor, greater loss of hydrogen to space, the gradual breakdown of conditions that allow surface oceans to survive. So Earth probably does have a Venus-like chapter somewhere in its distant future. Not because of the climate change unfolding over the next century, because stars evolve, and when we follow that process forward, we discover that the question is no longer whether Earth can remain habitable forever. It cannot. The real question becomes how a living ocean world finally reaches the point of no return. The point of no return does not begin with oceans suddenly boiling. It begins much more quietly. The sun gets brighter. Our star is not burning in the ordinary sense. Deep inside its core, hydrogen nuclei are being fused into helium. That process releases the energy that eventually reaches Earth as sunlight. But fusion also changes the internal composition of the sun. As helium accumulates in the core, conditions there gradually adjust. The core contracts and heats. Fusion proceeds under increasingly intense conditions. And over immense spans of time, the sun's luminosity slowly increases. This has already been happening for billions of years. The young sun was significantly fainter than the sun above us today, yet geological evidence shows that liquid water existed on early Earth, despite receiving less solar energy. That puzzle is known as the faint young sun problem. Earth's ancient atmosphere was different. Greenhouse gases, surface conditions, clouds, biological evolution, and other factors helped keep temperatures high enough for liquid water, even when the sun supplied less energy. But the direction of stellar evolution is clear. The problem facing the distant future is the opposite one. The sun will continue brightening. Earth will receive progressively more energy. And unlike human greenhouse emissions, this forcing cannot be negotiated with, reduced by policy, or reversed by changing technology. It is built into the life cycle of the star. At first, the changes would be gradual. A somewhat brighter sun would increase evaporation. A warmer atmosphere would hold more water vapor. Because water vapor absorbs infrared radiation, the greenhouse effect would strengthen. Temperatures would rise further. But remember what happens to water vapor in Earth's atmosphere today? Most of it remains relatively low. The upper atmosphere is extremely dry because the cold trap prevents large quantities of water from routinely reaching the stratosphere. That barrier is one reason Earth has retained its oceans for so long. In a warmer future, however, the cold trap becomes less effective. More water reaches higher altitudes. The stratosphere becomes wetter. And once water molecules reach regions exposed to energetic ultraviolet radiation, the same process we discussed on Venus begins to matter for Earth. The molecules can be broken apart. Hydrogen can escape. The ocean does not have to boil for the planet to start losing it permanently. This is the moist greenhouse problem. It is one of the most important distinctions in the entire story. A moist greenhouse is not necessarily a runaway greenhouse. The surface can still possess liquid water. The planet can still radiate enough energy to space to remain in approximate thermal balance. Yet the upper atmosphere becomes wet enough that hydrogen escape can drain the planet's water inventory over geological timescales. The catastrophe, if we can call something lasting millions of years a catastrophe, begins while oceans still exist. That may sound slow enough to be irrelevant. For humanity, it is. For a planet, it is decisive. Once hydrogen escapes into space, there is no global process waiting to pull it back down. Earth would gradually become drier. As water retreats, the climate system would change again. Weathering patterns would shift. Vegetation would decline under increasingly hostile temperatures and carbon dioxide conditions. The carbon cycle would reorganize. Ocean circulation would weaken as oceans themselves diminished. Life might retreat toward increasingly limited refuges. And this future would not arrive everywhere at once. Habitability would contract. First for large animals and complex ecosystems, then for increasingly heat-sensitive organisms, eventually, perhaps, for most surface life. Microbial life could persist far longer in isolated environments, underground, at high elevations, or in whatever liquid water refuges remained. Earth could remain technically inhabited long after it ceased resembling the living planet we know. This is another reason habitable can be deceptive. The final bacterium and a global forest both make a world inhabited, but they represent profoundly different planets. As solar luminosity continues increasing, the climate may eventually approach an even more extreme threshold. Here the behavior of water vapor becomes crucial. A planet loses energy to space primarily through infrared radiation, increase its surface temperature and, under ordinary circumstances, it radiates more energy outward. That is a powerful stabilizing response. Heating makes cooling stronger. But a thick water vapor atmosphere complicates the picture. As the atmosphere becomes increasingly opaque to infrared radiation, the altitude from which heat can effectively escape moves upward. At those high levels, temperature is controlled by atmospheric structure rather than simply by the furnace developing below. Under certain conditions, there is a limit to how much outgoing thermal radiation a water-rich atmosphere can emit efficiently. This is often associated with the runaway greenhouse threshold. If a planet absorbs more stellar energy than it can radiate back to space, while maintaining liquid surface water, then the ordinary route toward equilibrium fails. Additional heating produces additional evaporation. Additional evaporation increases atmospheric water vapor. The greenhouse strengthens. More of the ocean moves into the atmosphere, and the surface gets hotter. This is the feedback capable of destroying an ocean world. But even here, the exact future of Earth is not represented by one universally agreed date. Climate models differ in their treatment of clouds, atmospheric circulation, water absorption, and other important processes. Estimates of when Earth could leave its current state therefore depend on the model and on exactly what threshold we mean. Complex life could face severe limits before the oceans disappear. Photosynthesis could become difficult under changing carbon dioxide conditions before Earth reaches a moist greenhouse. Habitability for different organisms could end at radically different times. The transition is not one countdown clock. It is a sequence of losses, and it unfolds on a timescale of hundreds of millions to perhaps around 1 billion years for major habitability changes, not centuries. This needs to be kept separate from the warming happening now. Humanity is increasing greenhouse gases extremely rapidly. That is pushing global temperatures upward and increasing serious risks to ecosystems, infrastructure, water supplies, coastlines, agriculture, and human health. But current anthropogenic climate change and the eventual solar-driven destruction of Earth's oceans are different phenomena, operating at radically different scales. One does not need to exaggerate one to understand the danger of the other. There is no credible reason to tell people that ordinary fossil fuel emissions are about to boil the oceans. There are very strong reasons to reduce greenhouse emissions without making that claim. This distinction also helps us understand Venus. If the Sun naturally becomes brighter with age, then a rocky planet closer to it encounters these thresholds earlier. Venus orbits at roughly 72% of Earth's distance from the Sun. Because the intensity of sunlight increases strongly as distance decreases, Venus receives nearly twice the solar energy Earth does at the top of its atmosphere. That difference is enormous. Whatever water Venus began with, it lived much closer to the inner edge of conditions where stable surface oceans are possible. If ancient reflective clouds protected it, that protection had limits. If the young planet never condensed oceans, then its proximity to the Sun may have prevented an Earth-like beginning almost immediately. Either way, Venus was playing a harder game. Earth had more room, but not infinite room. This idea leads to one of astronomy's most famous concepts, the habitable zone. At first glance, the definition sounds reassuringly simple. The range of distances around a star where liquid water could exist on the surface of a rocky planet. But Venus immediately exposes the weakness in treating that zone like a fixed green ring around a star. Distance does not determine destiny. Atmosphere matters. Planetary mass matters. Clouds matter. Rotation matters. Geology matters. Water inventory matters. The history of the star matters. A planet can orbit within a nominal habitable zone and still be frozen, airless, suffocating, or overheated. And a planet near its boundary may change dramatically as its star evolves. The habitable zone itself moves. As the sun brightens, its inner edge gradually shifts outward. Earth does not need to move toward Venus. In a physical sense, Venus-like conditions can move toward Earth. Very slowly, almost imperceptibly, but relentlessly. And this changes how we should think about the two planets. Earth and Venus are not simply a success and a failure. They may represent different moments along trajectories available to rocky worlds under different levels of stellar heating. One preserved its oceans. One lost them. One remains blue. One became a world where carbon dioxide dominates the sky and water survives only in traces. Yet, if we want to know exactly why their histories separated, the answer may depend on something surprisingly specific. Not just how much sunlight each planet received, but when the first rain was able to fall. That first rain may have been one of the most consequential events in the history of either planet. Go back far enough, and neither Earth nor Venus looked remotely like the worlds we know today. The young solar system was violent. Planets were assembling through collisions between smaller bodies. Every major impact converted enormous amounts of kinetic energy into heat. Radioactive elements released additional energy from inside the growing planets. Dense materials sank toward their centers, lighter rock rose above them, entire surfaces could melt. For a time, early Earth may have possessed a magma ocean. Venus almost certainly passed through similarly extreme conditions. Above those molten surfaces hung atmospheres unlike anything surrounding either planet today. Water, carbon dioxide, nitrogen, sulfur compounds, and other volatile substances could be released from hot rock as planetary interiors differentiated and cooled. Large impacts could add volatiles, remove them, or temporarily vaporize portions of the surface. The first atmosphere was not necessarily the atmosphere that survived, and the first water was not necessarily an ocean. Much of it may initially have existed as steam. This is where distance from the sun begins to influence history in a very specific way. A cooling rocky planet can radiate energy into space. If the surface becomes cool enough and atmospheric pressure permits it, water vapor can condense. Cloud droplets form. Rain begins. Rain reaches hot rock and evaporates. More rain falls. The surface cools further. Over time, stable bodies of liquid water can accumulate. That transition changes almost everything. On Earth, geological evidence tells us that liquid water appeared very early. Ancient zircon crystals, some more than 4 billion years old, contain chemical signatures consistent with interaction between their parent materials and liquid water near Earth's surface. The exact geography of that early world is unknown. We cannot draw its coastlines. But Earth seems to have cooled enough for surface water astonishingly early in its history. Now place Venus beside it. If Venus remained just hot enough that steam could not efficiently condense, then the consequences would have cascaded. A steam-rich atmosphere is a powerful greenhouse. Water vapor traps heat. Trapped heat delays cooling. Delayed cooling keeps water in the atmosphere. Water remaining in the atmosphere strengthens the greenhouse. A planet trying to cool can therefore become caught in a competition between losing heat to space and retaining heat beneath its own vapor. This is not yet the modern Venusian atmosphere. It is something earlier. A world surrounded by the ingredients of an ocean, but unable to put that ocean on the ground. And that distinction may decide whether a rocky planet gets a second chance. If Earth's steam condensed, then liquid water could begin transforming the crust. Rain could react with rock. Dissolved minerals could move into oceans. Carbon dioxide could participate in chemical weathering. The atmosphere could begin exchanging carbon with geological reservoirs far more efficiently. The greenhouse could weaken. Cooling could reinforce further condensation. The planet would be moving away from the steam state. Venus may have moved the other way. If sunlight kept the lower atmosphere and surface too warm, water vapor could remain exposed high above the planet. Ultraviolet radiation would break apart molecules. Hydrogen would escape. The inventory of potential ocean water would shrink before a permanent ocean ever became established. The longer this continued, the harder recovery became. This creates a striking possibility. The difference between Earth and Venus may not require a beautiful blue Venus suddenly turning into hell. Perhaps the decisive divergence happened before either planet looked familiar. Earth crossed a condensation threshold. Venus failed to cross it. One world got rain. The other kept steam. And billions of years of planetary evolution followed from that early separation. But this is only one possibility. Climate simulations have shown that Venus might also have cooled enough for liquid water, especially if atmospheric circulation produced thick, reflective clouds over the hemisphere facing the Sun. Its slow rotation becomes important again here. On a rapidly rotating planet like Earth, weather systems are strongly shaped by the Coriolis effect. Atmospheric circulation breaks into multiple large-scale patterns. A slowly rotating planet behaves differently. Heating can produce enormous circulation cells extending across much of the world. Moist air rising beneath intense sunlight can generate thick cloud cover near the subsolar region. Those clouds reflect energy. Enough reflection can substantially reduce how much sunlight reaches the surface. So the same slow rotation that makes modern Venus seem bizarre may once have helped protect it from the Sun. Some models have found that even ancient Venus receiving much stronger sunlight than early Earth could potentially sustain moderate temperatures under favourable atmospheric and surface conditions. If true, the first rain may indeed have fallen there. Perhaps repeatedly. Perhaps for hundreds of millions of years. Potentially longer. And now the mystery becomes much harder. Because if oceans formed, something later removed them, the Sun brightening over time is one candidate. As incoming energy increased, evaporation would intensify. The atmosphere would contain more water. The planet could move toward a moist greenhouse. Hydrogen loss would accelerate. But solar evolution is gradual. It does not naturally produce a sharp catastrophe on a particular afternoon. So researchers have considered whether geology supplied an additional push. Venus is covered by volcanic terrain. Its interior has released enormous quantities of material throughout its history. Suppose an already warm Venus entered a period of exceptional volcanic activity. Large volumes of carbon dioxide could accumulate in the atmosphere. Sulfur gases could alter clouds. Lava could cover weathered surfaces and expose fresh rock, while at the same time massive eruptions could disturb the existing climate-carbon balance. If the planet still possessed oceans, warmer conditions would increase evaporation. If atmospheric water increased enough, hydrogen escape would intensify. As oceans shrank, weathering could decline. Carbon dioxide removal would weaken. Volcanic carbon could remain in the atmosphere longer. A geological event would then become a climatic event. And the climatic event could become a hydrological collapse. There is a brutal asymmetry here. Destroying an ocean can be easier than rebuilding one. Once water is merely evaporated, cooling can return it to the surface. But once hydrogen escapes to space, cooling cannot recreate the missing atoms. The planet has suffered an irreversible loss of material. This is why atmospheric escape is so central to Venus. It converts climate change into planetary evolution. Temperature determines where water resides. Ultraviolet light changes what the water is made of. Gravity and atmospheric physics determine what escapes. Geology determines what gases replace it. Over time, the planet itself becomes chemically different, and there may be another consequence of losing oceans that reaches deep beneath the surface. On Earth, water may influence how rocks deform and melt. Water lowers melting temperatures in some geological settings. It participates in mineral reactions. It is carried into the mantle at subduction zones and returned through volcanism. Plate tectonics itself depends on many factors, and scientists do not reduce it to water alone. But water changes rock mechanics. A dry Venusian lithosphere may therefore behave differently from Earth's wet tectonic system. This raises a profound chicken and egg problem. Did Venus lose its oceans partly because it lacked Earth-like plate tectonics? Or did it fail to develop or maintain Earth-like tectonics partly because it lost its water? We do not yet have a clean answer. That is exactly the kind of feedback planetary scientists are trying to untangle. Earth's moving plates help recycle carbon. Water influences the properties of rocks involved in that recycling. Climate determines whether water survives. Carbon influences climate. Interior evolution influences volcanism. Nothing operates alone. So the divergence between Earth and Venus may not have come from one fatal switch. It may have emerged from a chain in which each difference made the next difference larger. A little more sunlight, a little more atmospheric water, a little more hydrogen escape, a little less surface water, a weaker long-term carbon sink, more carbon dioxide overhead, more warming. Eventually, the two neighbouring worlds no longer look like variations of the same planet. They look like opposites. This is why Venus matters, beyond our solar system. Astronomers are beginning to discover rocky planets around other stars in enormous numbers. Some orbit where temperatures might allow liquid water. Some receive radiation comparable to Earth. Others receive something closer to Venus. From dozens or hundreds of light years away, however, we may never see their surfaces directly. We will see atmospheres, spectra, clouds, gases, and faint planetary signals buried inside starlight. To decide whether one of those distant worlds is another Earth, we first need to understand how easily an Earth-sized planet can become another Venus. Because the universe may be full of worlds that look habitable from a distance, and some of them may already have lost their first rain, and that possibility changes the way we search for life. For decades, the phrase Earth-like planet often meant something fairly simple in public imagination. A small rocky world, roughly Earth-sized, orbiting at a distance where liquid water might exist. That sounded like enough. Venus proves that it is not. Venus is almost the same size as Earth. Its surface gravity is similar. It is made largely from the same broad categories of rock and metal. It formed in the same planetary system from the same primordial disk of material. If we discovered Venus around another star and knew only its radius, mass, and orbit, we might be tempted to call it Earth's cousin. Technically, that would be true. Climatically, it would be almost meaningless. This is why astronomers now talk increasingly about the Venus zone as well as the habitable zone. The idea is not that every planet inside a particular line becomes identical to Venus. Instead, it gives researchers a framework for asking where rocky worlds may receive enough stellar energy to enter extreme greenhouse states. That matters because many of the rocky exoplanets we discover are easier to find when they orbit close to their stars. A planet near its star passes in front of that star more frequently from our viewpoint. If we use the transit method, those repeated crossings give us more opportunities to detect the tiny dip in starlight. Close-in planets also exert stronger gravitational effects on their stars, making them easier targets for radial velocity measurements. Our detection methods therefore create a natural bias. We find many hot worlds. Some may be scorched rocks with little atmosphere. Others may be wrapped in thick gases. And some may be genuine exovenuses. The problem is identifying which is which. From dozens of light years away, no spacecraft is going to descend through their clouds anytime soon. We have to use light. When a planet passes in front of its star, a small fraction of starlight may filter through the outer edge of its atmosphere. Molecules absorb particular wavelengths. With sensitive enough instruments, those absorption patterns can reveal atmospheric composition. For other worlds, astronomers can study heat emitted from the planet, or compare the system before and during an eclipse when the planet passes behind the star. Each technique is extremely difficult. The planet is faint. The star is bright. Clouds can hide atmospheric layers. Different gases can produce overlapping spectral features. And the signal from a small rocky planet can be tiny. Yet this is where Venus becomes invaluable. If we cannot interpret the atmosphere of the Venus next door with confidence, how can we hope to interpret a rocky world 50 light years away? Suppose a distant planet shows abundant carbon dioxide. Is that automatically evidence of a dead Venus-like climate? Not necessarily. Earth has carbon dioxide. Mars has carbon dioxide. Early Earth probably had much more of it than today. The climatic impact depends on abundance, atmospheric pressure, stellar radiation, clouds, other gases, and the presence or absence of surface reservoirs. Suppose we detect water vapor. That sounds more promising. But even water vapor does not prove oceans exist below. A world undergoing intense water loss could have large quantities of vapor in its atmosphere, precisely because its surface water is being destroyed. The same molecule could indicate habitability in one context and climate collapse in another. Oxygen creates an even more dangerous ambiguity. On Earth, atmospheric oxygen is overwhelmingly associated with life. Photosynthetic organisms transformed our planet by releasing it over geological time. So oxygen has long been discussed as a possible biosignature on exoplanets. But planetary processes can produce oxygen without biology. If ultraviolet radiation breaks apart water molecules and hydrogen escapes to space, oxygen can remain behind. Under some conditions, a planet losing an ocean could build substantial abiotic oxygen. Imagine the mistake. We detect oxygen around a distant rocky planet. We celebrate a possible living world. But what we are actually seeing is the residue of an ocean that died. Venus helps teach us how to avoid that trap. Biosignatures cannot be interpreted one molecule at a time. They require context, water, carbon dioxide, carbon monoxide, oxygen, methane, atmospheric pressure, cloud properties, stellar ultraviolet radiation, planetary temperature. All of these pieces tell a larger story. And sometimes the most important evidence may come from combinations of gases that should not coexist for long without being continuously replenished. The same logic applies to identifying dead worlds. A thick carbon dioxide atmosphere combined with evidence of extreme temperature and little accessible water would point toward one history. A dry, oxygen-rich atmosphere around a strongly irradiated world might point toward another. An atmosphere with water vapor, but no clear surface ocean signature, might demand caution. This is planetary forensics at interstellar distance. And the star itself is part of the crime scene. Our Sun is relatively stable compared with many smaller stars. Red dwarfs are particularly interesting because they are the most common stars in the galaxy, and their small size makes Earth-sized planets easier to detect. But young red dwarfs can be extremely active. They produce powerful flares. They emit energetic ultraviolet and X-ray radiation. And because they are dim, their habitable zones lie close to the star. That creates an uncomfortable combination. A planet can receive a moderate total amount of energy while orbiting close enough to endure intense high-energy radiation. Early in the star's life, it may also experience a prolonged period of elevated luminosity compared with the star's later stable state. A planet that eventually ends up in the habitable zone could therefore have spent its youth under conditions capable of evaporating large amounts of water. By the time the star settles down, the planet may already be dry. Its orbit says habitable. Its history says otherwise. Again, Venus provides the warning. Where a planet is now does not tell us what it survived before now. This is why planetary scientists increasingly need evolutionary histories rather than static labels. Did the world form with a large water inventory? How much atmosphere did it begin with? How active was its star? Did it possess a magnetic field? How quickly did its interior cool? Did oceans condense? Could carbon move into rock? Was volcanism steady or catastrophic? Did the planet rotate quickly or slowly? Did clouds protect it or warm it? Each answer modifies the next. That makes the search for another Earth much more difficult. It also makes it far more interesting. We are not merely searching for blue dots at comfortable distances. We are searching for worlds that have successfully maintained a particular planetary state across billions of years. Earth's present habitability is an achievement of history. Not intention, not destiny, history. A sequence of physical events happened in a way that preserved surface water long enough for life to emerge, transform the atmosphere, diversify, survive catastrophes, and eventually become capable of asking why the neighbouring planet failed. Venus may have followed the same path briefly, or it may never have started down it. Either answer would reshape how we estimate the abundance of habitable worlds. If Venus maintained oceans for billions of years before losing them, then habitable planets may be common but temporary. If Venus was doomed almost immediately, despite being so similar to Earth, then the conditions required for stable oceans may be narrower than they appear. This is why resolving Venus's history is not a side project in planetary science. It is part of the search for life in the universe. Before we can confidently identify another Earth, we have to learn how to recognize another Venus. And there is an even harder problem. From far away, a young Venus before its final transformation might have looked exactly like the planet we were hoping to find. Blue water, clouds, a moderate surface, perhaps even chemistry compatible with life. Then the star brightens. The oceans begin retreating. The atmosphere changes, and a world that once satisfied every simple definition of habitability crosses a boundary that no telescope watching a single moment in time could predict. That forces us to ask a different question about Earth. Not simply whether Earth is habitable today, not even whether human activity can damage that habitability, but why our planet has remained on the favourable side of those boundaries for so long. Part of the answer may lie in water and geology, part in distance from the sun, part in chance, and part may lie in an event so ancient and violent that its traces are still circling Earth every night. The Moon. Because Earth did not form alone, and the collision that gave us our enormous satellite may have altered the planet's climate history in ways we are still trying to understand. The Moon is so familiar that it is easy to forget how unusual it is. Compared with its planet, it is enormous. Most moons in the solar system are tiny relative to the worlds they orbit. Earth's moon is different. Its diameter is more than 1/4 of Earth's, and the two bodies are connected by a gravitational relationship that has been evolving for billions of years. That relationship began violently. The leading explanation for the Moon's origin is that early Earth was struck by a planetary body often called Theia, probably during the chaotic final stages of terrestrial planet formation. The collision was colossal. Material from the impactor and the young Earth was thrown into orbit. Some of that debris eventually assembled into the Moon. The details remain under active investigation. Scientists continue debating the impact geometry, the relative contributions of Earth and Theia, how thoroughly their materials mixed, and how the system evolved immediately afterward. But whatever the exact sequence, Earth emerged from its formation history with something Venus did not: a very large satellite. And that satellite changed the planet. One effect involves Earth's axial tilt. Our planet does not rotate perfectly upright relative to its orbit. Its axis is tilted by about 23.5 degrees. That tilt produces the seasons. More importantly, over very long timescales, the gravitational influence of the Moon helps modify how Earth's orientation evolves. Without the Moon, Earth's axial behavior could be different. This has sometimes been simplified into a dramatic claim that the Moon prevents Earth from tumbling chaotically and therefore saved life. Reality is more complicated. Numerical studies show that Earth's obliquity would not necessarily become completely random without the Moon, and the exact behavior depends on gravitational interactions with the other planets and on Earth's rotation rate. So the Moon should not be treated as a magical climate stabilizer. But it does matter. It changes the frequencies and amplitudes of Earth's rotational variations. And because axial tilt influences how sunlight is distributed across latitude and season, changes in obliquity can influence climate. Earth's climate therefore does not depend only on how much sunlight reaches the planet. It also depends on where that energy arrives and how its distribution changes through time. Venus presents the opposite extreme. Its rotation is extraordinarily slow and retrograde. If viewed from above the solar system's north pole, most planets rotate counterclockwise. Venus turns the other way. Why? We do not know with certainty. Large impacts early in its history could have changed its spin. Gravitational tides raised by the Sun could have modified rotation over immense periods. Atmospheric tides may also have played a role. The present rotation may therefore be the product of a long competition between the interior, atmosphere, and Sun. And rotation can affect climate profoundly. It changes wind patterns. It changes the Coriolis force. It changes where clouds accumulate. It changes the length of day and night. It changes how efficiently heat moves across the globe. This is why ancient Venus climate models pay so much attention to its spin. A slowly rotating wet Venus could potentially develop thick reflective clouds over the region receiving the strongest sunlight. Those clouds might cool the planet. But we do not know whether Venus rotated that slowly while it still had substantial water. Its modern spin cannot simply be projected unchanged back 4 billion years. The rotation itself evolved. The Moon gives Earth another major influence: tides. The Moon's gravity pulls unevenly on Earth, deforming the oceans and even the solid planet. The Sun also raises tides, but the Moon provides the dominant lunar contribution to the familiar tidal cycle. Those tides dissipate energy. The result is subtle but relentless. Earth's rotation gradually slows. The Moon gradually moves farther away. Early Earth rotated much faster than it does today. Days were shorter. The Moon was closer. Tides were stronger. Over billions of years, angular momentum has been redistributed through the Earth-Moon system. That means the planet on which life began was not rotating like the Earth beneath us now. Its atmospheric circulation was different. Its ocean dynamics were different. Its tides could have been dramatically stronger. And those differences may have mattered for biology. Tidal environments have sometimes been proposed as useful settings for prebiotic chemistry because repeated wetting and drying can concentrate molecules that would otherwise remain diluted. Other origin of life scenarios emphasize hydrothermal systems, freshwater environments, mineral surfaces, ice, or combinations of settings. We do not know where life began. So again, caution matters. The Moon may have influenced environments in which early chemistry occurred. That is not the same as proving that life required a large moon, but the broader lesson is difficult to escape. Planetary habitability depends on architecture. Not merely the planet, its moon, neighboring planets, impacts, rotation, star, and orbital history can all influence the climate state we eventually observe. Earth's giant impact may have changed its rotation. It created the moon. It released enormous heat. It may have altered the distribution of volatile materials. It may even have influenced the later behavior of Earth's mantle and core. We cannot rerun the solar system without that collision to see what would have happened. But we can compare outcomes. Venus has no moon. Mars has 2 tiny moons. Mercury has none. Earth has one enormous companion. And Earth is the only planet among them with stable surface oceans today. That correlation is intriguing. It is not proof of causation. This distinction matters because habitability research is full of tempting stories. Earth has a large moon, therefore large moons are required. Earth has plate tectonics, therefore plate tectonics is required. Earth has a magnetic field, therefore magnetic fields are required. Earth has continents, therefore continents are required. Each statement takes something associated with our own inhabited planet and quietly turns it into a universal law. Nature may not be so restrictive. There could be habitable planets without large moons. There could be ocean worlds with different tectonic regimes. There could be planets without strong global magnetic fields that still maintain atmospheres. There could be living worlds that would look profoundly unfamiliar beside Earth. Venus is valuable because it forces us to test these assumptions. It gives us a second large rocky planet built close to the same star. And almost every comparison produces another uncertainty. Why did Earth develop long-lived plate tectonics, while Venus apparently did not? Why did Earth retain so much water? Why did Venus rotate backward? How different were their earliest atmospheres? Did the moon matter decisively, modestly, or mostly indirectly? Which differences were causes, and which were consequences? This is where the story stops looking like a single chain and starts looking like a web. Perhaps Earth retained water partly because it was farther from the Sun. That water may have influenced rock mechanics and tectonics. Tectonics helped recycle carbon. Carbon cycling helped regulate temperature. Moderate temperatures helped retain water. The moon influenced rotation and tides. Rotation influenced atmospheric circulation. Life eventually altered atmospheric chemistry and weathering. Each process affected others. Venus may have developed a different web. Greater solar heating. Different cloud behavior. Water loss. Different crustal evolution. Slow retrograde rotation. Massive atmospheric carbon storage. Continued volcanism. No stable surface ocean to regulate the system. Once enough connections changed, comparing one isolated feature became almost meaningless. There was no single switch labelled Earth and Venus. There were histories, and history contains accidents. A giant impact at a slightly different angle, a different amount of delivered water, a longer-lived magma ocean, a change in volcanic outgassing, a different initial spin. None of those possibilities means planetary science becomes unknowable. It means we have to identify which processes leave measurable evidence. That is why Venus is about to become such an important target again. Its atmosphere can preserve isotopic history. Its surface can preserve geological history. Radar can reveal active deformation and volcanism. Measurements of its highlands may reveal whether ancient crust ever interacted with significant liquid water. And if those observations finally tell us whether Venus began wet or dry, they will eliminate entire branches of its possible history. Then the question in our title becomes sharper. Could Earth be next? On human timescales, not in the Venusian sense. On stellar timescales, eventually. But there is another version of that question that does concern us now. Not whether Earth can become Venus, whether studying Venus can tell us which parts of a habitable planet are robust and which can be lost far more easily than they appear. To answer that, we have to separate the myths surrounding Venus from the warnings the planet actually gives us. The first myth is also the easiest to believe. Venus became hell because it has too much carbon dioxide. That statement is not exactly wrong. It is incomplete. Carbon dioxide dominates the Venusian atmosphere and plays a central role in maintaining its extraordinary surface temperature. Remove that massive atmosphere and the planet would not remain the furnace we see today. But carbon dioxide is the ending of the story as much as it is part of the cause. We still have to explain why so much carbon ended up in the atmosphere, why Venus lost nearly all of its accessible water, why carbon was not stored in surface reservoirs the way enormous quantities are stored on Earth, and how volcanism, atmospheric escape, sunlight, and geological evolution interacted over billions of years. Simply pointing at carbon dioxide skips the planetary machinery that put it there. Earth demonstrates why that distinction matters. Our planet contains vastly more carbon than the amount currently floating in the atmosphere. Much of it is locked in rocks. Some is dissolved in oceans. Some moves through soils, ecosystems, sediments, and the mantle. The atmosphere is only one reservoir. If we compare Earth and Venus using atmospheric carbon alone, we are comparing where carbon happens to be stored today, rather than how the two planetary carbon systems work. Venus may have once stored more carbon in its crust. It may have once possessed water capable of accelerating chemical interactions between atmosphere and rock. Or it may never have developed an Earth-like carbon cycle at all. Those possibilities lead to different histories, and we do not yet know which one is correct. The second myth is that Venus proves any greenhouse warming inevitably runs away. It does not. Greenhouse warming is a spectrum of physical states. Earth's natural greenhouse effect makes the planet warm enough for oceans, increase greenhouse gas concentrations, and the surface warms further. That additional warming can activate feedbacks, including increased atmospheric water vapor and reduced ice cover. But a positive feedback is not automatically an infinite feedback. That distinction is critical. Suppose warming melts some reflective ice. The darker surface absorbs more sunlight. That amplifies the original warming. But eventually the amount of ice available to melt becomes smaller. The feedback does not continue without limit. Water vapor works similarly within ordinary Earth climate conditions. Warmer air generally contains more water vapor. That vapor strengthens greenhouse warming. But the climate still radiates energy to space, and other processes continue operating. A full runaway greenhouse requires a much more extreme breakdown in the normal balance between absorbed stellar energy and outgoing thermal radiation. Modern human-caused warming is dangerous without crossing that boundary. This is not a weaker warning. It is a more accurate one. If we tell people Earth is about to become Venus and the oceans fail to boil, the conclusion may be that climate science exaggerated the danger. But climate science never needs a 467-degree surface to justify concern. A few degrees of global warming can transform extremes across enormous regions because the global average hides much larger local changes. Heat waves intensify. Hydrological cycles shift. Ice retreats. Sea level rises. Ocean chemistry changes. Species are pushed beyond climatic ranges. Agricultural systems face combinations of heat, drought, flooding, and changing rainfall. The danger lies inside the Earth system we actually inhabit. We do not need to import Venusian conditions to make it serious. The third myth goes in the opposite direction. Because Earth will not become modern Venus from present human emissions, some people conclude that Venus has nothing useful to teach us about climate. That is equally mistaken. Venus is an experiment nature has already run. It shows what a thick greenhouse atmosphere can do. It shows that water inventories can be permanently depleted. It shows that where a planet stores carbon matters. It shows that climate cannot be separated cleanly from geology. And it shows that rocky planets similar in size can evolve toward radically different surface environments. We study extremes precisely because they reveal physical limits. Black holes help test gravity. Antarctic ice helps reconstruct ancient atmosphere. Supernovae reveal nuclear processes under conditions laboratories cannot reproduce. Venus tests climate physics in a regime Earth does not currently occupy. The fourth myth is that the runaway greenhouse is the only interesting threshold. It is not. A planet can undergo a moist greenhouse before a classical runaway state. An ice sheet can cross a stability threshold without the atmosphere crossing one. An ecosystem can collapse while global mean temperature remains far below anything Venusian. Ocean circulation can shift because of changes in temperature and salinity. Different components have different thresholds, different timescales, different degrees of reversibility. There is no single planetary red line behind which everything is safe and beyond which everything collapses at once. That is not how complex systems behave. The fifth myth is perhaps the most seductive of all. Venus is Earth's future. Eventually, in a very broad sense, perhaps something like that is true. As the sun brightens, Earth is expected to become increasingly hostile to surface oceans. Far in the future, our planet may lose much of its water and evolve toward conditions that share important features with Venus. But modern Venus is not a guaranteed frame-by-frame preview. Earth has a different mass, a different rotation, a large moon, different geological history, different atmospheric inventory, different surface chemistry, different biological history, and the future sun will continue evolving while Earth changes. Our distant end state may resemble Venus without reproducing it exactly. Planetary evolution rarely copies. It rhymes through physics. And then there is the myth that Venus must have suffered one spectacular apocalypse. It is easy to imagine. A blue Venus, oceans, clouds, perhaps a pleasant surface. Then volcanoes erupt across the entire planet. Carbon dioxide floods the sky. Temperatures race upward. Oceans boil. The world dies. It is cinematic. It may also be wrong. The transition could have taken millions of years, or tens of millions. Different mechanisms may have dominated at different stages. The loss of water could have begun long before the modern atmosphere formed. Volcanism could have occurred in pulses rather than one global event. Surface resurfacing may have been regional and episodic. There may never have been a singular moment when Venus became hell. Planetary catastrophes do not have to be sudden to be final. That may be the more important concept. Imagine an ocean shrinking so slowly that no observer living for a century would witness the entire transformation. Generation after generation experiences a slightly altered world. The upper atmosphere continues losing hydrogen. Carbon continues moving between interior, surface, and atmosphere. The sun continues brightening. Eventually, the planet reaches a state from which the earlier ocean cannot return. No explosion marks the boundary. No alarm sounds. The irreversible event is visible only when geological time is compressed. This is where Venus offers perhaps its strongest warning. Not that Earth is secretly one step from a runaway greenhouse. Not that one gas can destroy a world by itself. And not that every climate shift becomes unstoppable. The warning is that planetary environments are maintained by processes that operate on radically different clocks. Atmospheres can change quickly. Oceans respond more slowly. Ice sheets can continue adjusting for centuries. Rocks store carbon for millions of years. Stars brighten across billions. A system can therefore be pushed now and reveal part of its full response much later. That lag changes how we think about reversibility. If temperatures stabilize, some consequences may continue. If emissions stop, atmospheric carbon does not instantly disappear. If ice begins a long retreat, rebuilding it may require conditions sustained far beyond a human lifetime. Climate action, therefore, is not about preventing Earth from turning into Venus next Tuesday. It is about avoiding changes whose costs continue accumulating after the original decisions have passed into history. And Venus gives us a planet where history won. Whatever sequence brought it there, the original conditions are gone. The missing hydrogen is in space. The surface water is effectively absent. The atmosphere presses down with immense weight. Its old climate, if a mild one ever existed, cannot simply resume. That is what irreversible means on a planetary scale. But the strongest evidence for exactly how irreversible that transformation became may still be sitting beneath the clouds. Not in the atmosphere, in the oldest surviving pieces of Venusian crust. If those rocks contain the right minerals, they could finally tell us whether water once flowed across this world. And that would determine whether we are looking at a planet that was born hell or one that became it. The oldest rocks may decide between those two histories. That is why the highlands of Venus matter so much. Across parts of the planet are elevated regions of intensely deformed terrain known as tesserae. Radar images show ridges crossing other ridges, fractures cutting through older structures, and surfaces that appear to have experienced multiple episodes of deformation. They look complicated because they are complicated. And in planetary geology, complication can be valuable. A smooth volcanic plain may tell us about relatively recent lava. A battered, folded, fractured highland can preserve a much longer history. If tesserae formed before the widespread volcanic plains that dominate much of Venus today, then they may contain material from an earlier stage of the planet's evolution, possibly from the period when water was still present. This is where mineralogy becomes a time machine. Different rocks form under different conditions. Basalt, the volcanic rock common across Earth's oceanic crust, can form when mantle-derived magma cools. Venus is expected to possess enormous quantities of basaltic material because volcanism has resurfaced so much of the planet. But some scientists are especially interested in whether portions of the Venusian highlands could contain more silica-rich rocks. On Earth, rocks such as granite are strongly associated with geological processes that commonly involve water and extensive crustal reworking. That does not mean finding silica-rich rock on Venus would automatically prove ancient oceans. There are ways to create evolved magmas without Earth-like oceans or plate tectonics. But the composition would matter enormously. If ancient Venusian highlands turned out to contain continental-like felsic material, scientists would have to explain how that crust formed. Water would become one of the most important possibilities. We already have tantalizing hints. Spacecraft observations of Venus in near-infrared wavelengths have revealed differences in emissivity from some highland regions. Certain interpretations have suggested that these surfaces could differ compositionally from the younger basaltic plains. But remote sensing through Venus's atmosphere is difficult. The atmosphere absorbs and emits radiation. Clouds interfere. Surface temperatures affect spectral signals. And several different mineral combinations can sometimes reproduce similar measurements. So a hint is not a rock sample. That distinction defines the problem. From orbit, scientists can identify targets. To know what those targets truly are, we need much more precise measurements. Imagine a future probe descending toward one of these ancient regions. As it falls, it samples atmospheric gases. It measures noble gases and isotopes. It tracks temperature, pressure, winds, and chemistry. Then, near the surface, instruments analyze the rocks themselves. What elements are present? How much silicon? How much potassium? How much iron? What minerals can survive under Venusian conditions? Do their compositions resemble basaltic crust? Or has the rock undergone extensive differentiation? A few measurements could eliminate entire climate histories. Suppose the oldest accessible terrain is overwhelmingly basaltic and shows little evidence that water played a major role in its formation or alteration. That would not prove Venus never had oceans. Water leaves different signatures depending on duration, temperature, and rock type. Later volcanism can erase earlier evidence. Extreme heat can alter minerals. But the case for a long-lived Earth-like surface would become harder to establish. Now suppose the opposite. Suppose measurements identify rocks whose most plausible formation history requires substantial interaction with water or extensive wet crustal processing. Suddenly, ancient oceans would move from climate model possibility toward geological evidence. Then the question changes. We would know that Venus had once crossed the threshold Earth crossed. Steam condensed. Rain fell. Water interacted with rock. A fundamentally different climate existed. And somehow the planet lost it. That would make Venus one of the most important natural laboratories in all of planetary science. Because we would possess two nearby examples of initially wet, rocky worlds. One survived, one failed. Their divergence could be studied directly. There is another clue the rocks might hold. Oxidation. When ultraviolet radiation breaks apart water and hydrogen escapes, oxygen is left behind. Some of that oxygen can also escape, but some may react with surface minerals. Over enough time, the crust can act as a chemical sink. If Venus lost an enormous ancient ocean, then a correspondingly enormous amount of oxygen had to go somewhere. The surface may have absorbed part of it. Determining the oxidation state of ancient Venusian rocks could therefore help constrain how much water was destroyed and how the planet processed the oxygen left behind. Again, no single measurement gives a complete answer. Atmospheric isotope ratios tell us about escape. Surface mineralogy tells us about rock-water interaction. Oxidation tells us about oxygen sinks. Crater populations constrain surface ages. Radar reveals structures. Thermal observations can identify possible active volcanism. The story emerges only when those clues agree. And that is why Venus science has entered such an interesting period. For decades, Mars received much of the attention devoted to terrestrial planets. The reason is understandable. Mars has a surface we can see. Landers can survive for years. Rovers can drive across ancient lakebeds. Orbiters can map minerals directly. Sample may eventually be returned. Venus is much harder. Its clouds hide the ground. Its atmosphere complicates remote sensing. Its surface destroys conventional electronics quickly. The result is an enormous scientific imbalance. We have studied the colder, smaller neighbour in exquisite detail, while the planet most similar to Earth in size remains partially concealed. That is beginning to change. New mission concepts focus on different pieces of the Venus puzzle. NASA's Da Vinci mission is designed around atmospheric descent and high-resolution measurements of composition, including noble gases and isotopes. Its descent sphere is intended to travel through the atmosphere while collecting data that could help reconstruct Venus's origin and water loss history. Veritas, another NASA mission, is designed to use radar and spectroscopy from orbit to investigate the surface and interior, map topography, examine geological structures, and search for evidence of active processes. The European Space Agency's Envision mission is also intended to study Venus from orbit, connecting surface geology with atmospheric and interior processes. The details and schedules of missions can evolve. The scientific logic does not. One mission reads the atmosphere. Another reads the surface. Another examines how the two are connected. Together, they attack the central mystery from different directions. And that approach is necessary because Venus can fool us if we look at only one layer. A carbon dioxide atmosphere does not reveal when the carbon arrived. A dry surface does not reveal when the water disappeared. A volcanic plain does not reveal what older crust lies beneath it. A deuterium ratio does not reveal whether the missing water once formed a shallow sea or a deep global ocean. Each observation is a fragment. The goal is to turn fragments into chronology. First this happened, then this. Then the climate crossed this threshold. Then the atmosphere changed. Then the surface was resurfaced. If scientists can build that chronology, the phrase runaway greenhouse will stop being a broad label for Venus and become a testable historical mechanism. We may discover that Venus truly passed through a runaway state after long-lived oceans. We may discover that its water loss occurred mostly during an early steam atmosphere before stable seas ever formed. We may find an intermediate history that neither popular story captures well. Science is allowed to produce an answer less cinematic than the question. In fact, that is often where the most interesting truth lives. Because if Venus was born dry, Earth's success may depend on an unusually narrow set of early conditions. If Venus became dry much later, stable habitability may be more fragile over geological time. Those possibilities make opposite predictions about planets around other stars. One says getting oceans is difficult. The other says keeping them is difficult. And until we know which problem Venus encountered, we do not know which lesson to export to the galaxy. But even before those missions answer it, one fact is already clear. Venus did not merely become hot. It became trapped in a planetary state, maintained by the interaction of atmosphere, surface, sunlight, and lost water. That raises a final practical question for Earth. If our planet is nowhere near a Venus-style runaway today, what exactly should we fear from warming now? The answer is not the end of the oceans. It is the destabilization of the world that exists before that extreme, and that world contains thresholds much closer to us than Venus ever will be. Those closer thresholds are less spectacular than a boiling ocean. That is exactly why they matter. A runaway greenhouse is easy to imagine because it gives us a dramatic endpoint. The sky thickens, the oceans vanish, temperatures soar, the planet becomes unmistakably alien. Earth's nearer risks are harder to see, because the planet can still look like Earth while enormous changes are already locked in. The coastline moves. The forest changes species. A glacier retreats farther each decade. An ocean current weakens. Extreme heat that once appeared rarely becomes common enough to reshape how cities function. None of these produces a Venusian sky. All of them can alter human lives. Consider sea level. The ocean rises for more than one reason. As seawater warms, it expands. Mounting glaciers lose mass. The Greenland and Antarctic ice sheets contribute additional water. These processes respond on different timescales, which means sea level does not simply track the temperature of one particular year. The ocean stores heat. Ice sheets respond slowly. A warmer climate maintained long enough can commit the planet to changes that continue long after the initial forcing stops increasing. That word, commitment, is important. It does not necessarily mean every centimetre of future sea level rise is unavoidable today. It means the climate system can acquire momentum. Suppose atmospheric temperature stabilizes. That does not instantly cool the deep ocean. It does not instantly rebuild glaciers. It does not instantly restore an ice sheet to an earlier geometry. Large systems have inertia. Venus teaches us about planetary memory in an extreme form. Earth shows the same principle on scales that matter now. Take the Greenland ice sheet. Its surface gains ice through snowfall and loses mass through melting and the discharge of glaciers into the ocean. Warming changes that balance. As the ice surface lowers, parts of it can enter warmer air at lower elevations, which can encourage additional melting. Darkening from exposed land. Meltwater, dust, or biological material can also change how much sunlight is absorbed locally. The details are complex, and scientists do not describe the entire ice sheet as one simple switch. But the general point is clear. Ice can contain reinforcing processes. Antarctica brings different vulnerabilities. Much of the West Antarctic ice sheet rests on bedrock below sea level. In some regions, the bed slopes downward inland. Where relatively warm ocean water can reach floating ice shelves, those shelves may thin. Because ice shelves help restrain glaciers behind them, weakening them can allow land ice to move toward the ocean more rapidly. Again, this is not a Venus-style runaway. It is a completely different mechanism. That distinction should make it easier to understand, not easier to dismiss. There are many ways for a system to become difficult to reverse. The oceans contain another one. They have absorbed most of the excess heat accumulating in the climate system. That heat does not stay at the surface. Currents move it vertically and horizontally. Different ocean basins store and release energy over years, decades, and longer. This buffers atmospheric warming in the short term, but it also means the planet carries thermal memory beneath the waves. The ocean also absorbs carbon dioxide. That slows the increase of carbon dioxide in the atmosphere, which helps limit warming. But dissolved carbon dioxide changes seawater chemistry. It lowers pH and reduces carbonate ion availability, creating problems for organisms that build shells or skeletons from calcium carbonate. The same ocean is therefore providing a climate service while absorbing a chemical cost. Planetary systems rarely give us a benefit without another connection somewhere else. Forests offer another example. Vegetation removes carbon dioxide through photosynthesis. Trees store carbon in wood. Soils hold enormous carbon reservoirs. But forests also depend on climate, temperature, rainfall, fire frequency, drought, pests, land use. Change those conditions enough, and a forest may store less carbon or lose carbon to the atmosphere. That creates the possibility of feedback. Warming damages part of a carbon sink. The weakened sink removes less carbon dioxide. More carbon remains in the atmosphere. That contributes additional warming. But once again, language matters. This does not mean every forest on Earth is waiting to collapse simultaneously. Different ecosystems have different sensitivities. Some regions may become drier. Others may receive more rainfall. Species can migrate where geography and human land use allow it. Ecological change is uneven. The real world is messier than a single tipping point graphic. Permafrost shows the same complexity. Frozen soils across high northern latitudes contain large stores of organic carbon accumulated over long periods. When permafrost thaws, microbes can decompose previously frozen organic material and release carbon dioxide or methane. Those greenhouse gases can add to warming. This is a genuine feedback, but it is not a hidden bomb that detonates all at once. Permafrost exists across enormous areas with different soil types, ice content, hydrology, temperatures, and ecological conditions. Its response unfolds over time. That makes the risk less cinematic, not less real. And this is where the comparison with Venus becomes useful again. Venus represents the final dominance of reinforcing processes under conditions far outside modern Earth's range. Earth's present challenge is managing smaller feedbacks before they accumulate into larger commitments. There is no requirement that these feedbacks become infinite before they become expensive. A bridge does not need to collapse everywhere on Earth for infrastructure risk to matter. A crop does not need to fail globally for food prices to respond. The coral species does not need to vanish from every ocean before an ecosystem loses function. Climate damage is not binary. Neither is habitability. The same applies to reversibility. If atmospheric carbon dioxide begins declining after emissions fall, some climate effects can respond relatively quickly. Air pollution can improve rapidly when its sources are reduced. Some ecosystems can recover if pressures are removed. Other changes operate on much longer clocks. Deep ocean warming can persist. Sea level can remain elevated. Lost species do not return. A glacier that disappears cannot be restored simply by having one cool summer. This gives us three different ideas that are often confused. Stopping a forcing, stopping a response, reversing the damage. They are not the same thing. Turn off a stove, and the burner stops receiving energy immediately. A pot of water sitting on it does not instantly become cold. Climate contains many versions of that delay. Carbon dioxide makes the situation even more unusual because it is not removed from the atmosphere by one simple decay process. Some of the excess carbon is absorbed relatively quickly by land and ocean reservoirs. Some persists much longer. Returning the entire carbon climate system toward its previous state involves processes operating across many timescales. So decisions made over a few generations can influence conditions far beyond those generations. This is not because Earth is fragile like glass. Earth is extraordinarily resilient as a planet. It has survived asteroid impacts, massive volcanism, glaciations, warming events, mass extinctions. The planet keeps going. But resilience at the planetary level can be brutal. After the end Permian extinction, life eventually diversified again. That does not make the extinction harmless. After an ice sheet disappears, Earth remains a planet. That does not put the coastline back where our cities were built. After ecosystems reorganize, new ecosystems emerge. That does not restore the species that were lost. So when we ask whether Earth could be next, the most useful answer depends on what next means. Next Venus? No, not from present human greenhouse emissions. Next planet to experience major climate-driven disruption? We do not have to speculate. That process is already measurable. And because we understand the mechanism, we also know something Venus could never know about itself. The forcing is not entirely beyond our control. The sun's long-term brightening cannot be stopped. Ancient impacts could not be negotiated with. But human carbon emissions result from choices about energy, land, technology, industry, and policy. That makes our situation scientifically different from Venus in one final, crucial way. We are not merely observing a planetary feedback. We are part of the forcing, and that means the future does not branch from physics alone. It branches from what we do while the system is still capable of responding. That ability to influence the forcing is easy to underestimate. Climate change is sometimes described as if humanity has already pushed a giant machine into motion and can now do nothing except watch it accelerate. That is not how the physics works. Some consequences contain long delays. Some changes may become extremely difficult to reverse. But the amount of future warming still depends strongly on how much additional greenhouse gas we put into the atmosphere. That connection is one of the most important facts in the entire climate problem. Carbon dioxide accumulates. Every year that human activities release more carbon dioxide than natural and engineered processes remove, the atmospheric concentration remains elevated or increases. The climate system responds to that altered concentration by trapping more energy. So future temperature is not determined only by what humanity has emitted in the past. It depends on what comes next. This is where the concept of net zero becomes important. Net zero carbon dioxide does not mean all emissions suddenly disappear. It means remaining human carbon dioxide emissions are balanced by sustained carbon dioxide removals. Why does that matter? Because global warming from carbon dioxide is closely related to cumulative emissions. Add more carbon to the atmosphere, ocean, land system, and warming increases. Stop adding net carbon, and the dominant carbon dioxide-driven warming can approximately stop increasing, although different components of the climate system continue adjusting. That last part matters. Temperature stabilization is not the same as restoring the previous climate. Sea level may continue rising. Ice can continue responding. Deep oceans continue redistributing heat. Ecosystems continue adapting or declining. But avoiding additional warming still avoids additional damage. This sounds almost obvious when stated plainly, yet it destroys one of the most dangerous misconceptions about climate action. The idea that because some warming is already unavoidable, reducing emissions no longer matters. Imagine a road descending toward a cliff. If you have travelled halfway down it, The fact that you cannot instantly return to the top does not make the remaining distance irrelevant. Every fraction of additional warming changes risk. Not because there is one magical temperature where safety suddenly ends. Because higher temperatures progressively increase the probability and severity of many impacts. More extreme heat, more intense heavy rainfall in many regions, greater sea level commitment, greater ecosystem stress, greater ice loss. The climate does not reward all or nothing thinking. Physics operates continuously. Methane adds another layer. Methane is a powerful greenhouse gas, but it behaves differently from carbon dioxide. A methane molecule does not remain in the atmosphere for thousands of years in the same way a fraction of emitted carbon dioxide can influence the carbon cycle for extremely long periods. Atmospheric methane is chemically removed on a timescale of roughly a decade, although its effects and chemistry are more complicated than one number captures. That means reducing methane emissions can slow warming relatively quickly. If methane emissions fall substantially, atmospheric methane concentrations can respond on timescales relevant to people alive today. Carbon dioxide demands a different strategy because its accumulation is tied so strongly to total emissions. Different gases, different lifetimes, different mitigation logic. Again, one atmosphere does not mean one mechanism. Venus reinforces this lesson at an extreme scale. Its modern atmosphere is overwhelmingly carbon dioxide, but it also contains nitrogen, sulfur compounds, water vapor in trace amounts, and a complex cloud chemistry. The climate state emerges from the combination. Earth's atmosphere is also a mixture. Carbon dioxide receives enormous attention because human emissions have raised its concentration dramatically, and because it is the largest contributor to long-lived anthropogenic greenhouse forcing. But methane, nitrous oxide, ozone, aerosols, clouds, and land surface changes all affect the energy budget. Some human-produced particles actually reflect sunlight and temporarily mask part of the greenhouse warming. This creates an uncomfortable complication. Cleaning up air pollution can remove some of that cooling effect. That is not an argument for keeping dangerous air pollution. It is an example of why the climate system must be understood as a set of simultaneous forcings, rather than one dial. When sulfur pollution falls, health benefits can be immediate and enormous. But climate policy also has to account for the greenhouse warming that the pollution had partially concealed. The atmosphere keeps the full ledger. This is another place where Venus provides perspective. Sulfur on Venus helps form its brilliant cloud deck. Those clouds reflect sunlight strongly. Yet underneath them, the carbon dioxide atmosphere keeps the surface brutally hot. A reflective atmosphere is not automatically a cool surface. A greenhouse atmosphere is not automatically a runaway. Individual effects have to be placed inside the full energy balance. Earth is fortunate in another sense. We can measure that balance with extraordinary precision. Satellites observe incoming solar radiation and outgoing energy. Weather balloons sample atmospheric profiles. Ocean floats measure temperature and salinity deep beneath the surface. Ice cores preserve ancient atmospheres. Tree rings, corals, sediments, cave deposits, and fossils extend climate records into the past. The planet is being watched from the seafloor to orbit. This does not eliminate uncertainty. It reveals where the uncertainty is. Scientists cannot tell us the exact temperature of every city on every day decades from now. They can constrain global responses. They can test climate models against past and present changes. They can measure the fingerprints expected from greenhouse forcing. The lower atmosphere warms while the stratosphere cools. Oceans accumulate heat. Ice loses mass. Nighttime and seasonal patterns change. Those combined fingerprints matter because they distinguish greenhouse warming from explanations such as an increase in solar output. Science does not rest on one thermometer. It rests on converging evidence, and that brings us back to agency. The laws controlling greenhouse warming are not waiting to be discovered in the future. We already know enough to understand the direction of the response. More net greenhouse forcing produces more warming. Less future forcing produces less future warming than the alternative. That does not mean every climate projection will be exact. It means uncertainty is not our friend. If we do not know precisely how sensitive a vulnerable ice sheet or ecosystem will be, that uncertainty includes outcomes worse than the central estimate, as well as better ones. Uncertainty is a range, not an escape hatch. And there is another reason action matters even when some damage is irreversible. Adaptation has limits that depend on the amount and speed of change. A city can redesign drainage for heavier rainfall. Farmers can change crops. Buildings can be cooled more efficiently. Coastlines can be protected in some places. Early warning systems can reduce deaths from heat and storms. Infrastructure can be redesigned. But adaptation becomes harder as climate change grows. A small sea level rise may be managed with barriers or retreat in selected areas. Much larger long-term rises transform the question completely. Moderate heat can be addressed with building design and cooling. Extreme combinations of temperature and humidity can challenge outdoor labour and health even with adaptation. Mitigation and adaptation therefore solve different parts of the problem. Mitigation reduces how far the climate shifts. Adaptation helps us live with the shift that occurs. Neither replaces the other. Venus has no adaptation story. Once its atmosphere reached the state we see today, no biological engineering strategy could restore oceans through ordinary planetary processes. Earth is nowhere near that state. And precisely because we are not, choices still matter enormously. The future is not divided into a safe Earth and a Venus Earth. It contains many possible Earths. Some warmer, some much warmer, some with greater ice loss, some with less, some with more damaged ecosystems, some with more time to adapt. The differences between those futures are not cosmetic. They represent lives, coastlines, species, infrastructure, food systems and landscapes. And unlike Venus's ancient transformation, we can observe the forcing while it happens. We can quantify it. We can identify its source. We can change its future trajectory. That may be the strangest contrast between the two planets. Venus gives us a world whose climate history is mostly hidden. Earth gives us a world watching itself change in real time. So the final question is no longer whether Earth could become Venus tomorrow. It cannot. The question is what Venus teaches us about the value of staying far away from planetary boundaries before nature, rather than choice, takes control of what happens next. And to answer that, we need to return one last time to the surface beneath those yellow clouds. Beneath those clouds, nothing looks like a warning sign. There is no inscription in the rock saying where the oceans went. No preserved wave reaches a vanished shore. No crater marks the exact moment the climate crossed a boundary. There is only stone beneath an atmosphere almost entirely transformed from anything we would call familiar. That is what makes Venus so powerful. The evidence is incomplete, yet the outcome is absolute. Its surface is hot enough to melt lead. Its atmospheric pressure is crushing. Its clouds are made largely from sulfuric acid droplets. Its accessible water is almost gone. And an enormous quantity of carbon dioxide now surrounds the planet. Those facts are not models. They are the world we have measured. The uncertainty lies in the road that led there. Perhaps Venus began with a steam atmosphere that never fully condensed. In that history, the decisive failure occurred extraordinarily early. Earth cooled enough for rain. Venus did not. Water remained vulnerable in the atmosphere. Ultraviolet radiation broke it apart. Hydrogen escaped, and the planet lost much of its potential ocean before a stable ocean world could truly begin. If that is correct, Venus is not the corpse of another Earth. It is a planet that narrowly failed to become one. But perhaps the other history is closer to reality. Perhaps clouds reflected enough sunlight to protect a young Venus. Perhaps rain fell. Perhaps oceans occupied lowlands now buried beneath volcanic plains. Perhaps water interacted with ancient crust while the sun was dimmer and the atmosphere was fundamentally different. Then, as the sun brightened and geology evolved, the balance became harder to maintain. Evaporation increased. The upper atmosphere became wetter. Hydrogen escaped. Volcanism supplied carbon dioxide. Carbon cycling weakened as surface water disappeared. Feedbacks amplified the transformation. If that happened, Venus is something more unsettling. A formerly temperate world that lost the conditions that made it temperate. Right now, science cannot honestly choose between those broad histories with the confidence we want. That is not a failure. It is the frontier. Measurements of noble gases can constrain atmospheric origin and escape. Hydrogen isotopes can refine the story of water loss. Radar can reveal active geology. Ancient highlands may preserve minerals formed under conditions unlike the modern surface. Future observations can gradually remove possibilities until a chronology survives. And when that chronology emerges, it will tell us far more than what happened to one planet. It will tell us how fragile the inner edge of habitability really is. That phrase, inner edge, may be the most important idea Venus gives us. Habitability is not a circle drawn permanently around a star. It is a moving boundary created by atmospheric physics, geology, water, clouds, rotation, and stellar evolution. A planet can begin outside favorable conditions and move into them. It can begin inside them and leave. It can remain habitable for billions of years and still possess no guarantee of permanence. Earth is inside that story too. Today, we occupy the fortunate side of the comparison. Our oceans remain liquid. Rain reaches the ground. Carbon moves between atmosphere, ocean, rock, soil, life, and mantle. The climate system contains feedbacks that have helped keep surface conditions within a wide habitable range across immense spans of time. Our atmosphere is thin compared with Venus. Our surface is cool enough for an active hydrological cycle. Life has become woven into the planet's chemistry. But none of that means Earth is invulnerable. It means Earth occupies a different climate regime. And that is the answer to the second half of our question. Could Earth be next? If by next we mean that industrial greenhouse emissions will soon transform Earth into modern Venus, the answer is no. That is not supported by climate physics. The oceans are not about to enter a classical Venus-style runaway greenhouse because humanity burns fossil fuels. We should reject that claim clearly. A false warning does not strengthen a real one. It weakens it. But if next means can Earth's climate be pushed far enough to cause severe, long-lived, and in some cases effectively irreversible changes on human timescales, then the answer is already yes. We know because Earth has done it before. Its geological record contains abrupt warming events, mass extinctions, enormous changes in sea level, ice ages, ocean chemistry disruptions, ecological reorganizations. The planet survives. That is almost never the relevant standard. The relevant standard is what happens to the organisms, societies, infrastructure, coastlines, food systems, and ecosystems living through the transition. Earth does not have to become Venus for the consequences to become profound. And there is a final distinction. Venus could not choose. Whatever pushed its climate across its ancient boundaries, solar heating, water loss, atmospheric escape, volcanism, geological evolution, or some combination, there was no observer standing above the clouds capable of understanding the energy balance and altering the forcing. Earth has produced a species has emerged that can measure carbon dioxide in ancient ice. Map heat stored thousands of meters below the ocean surface. Watch ice sheets lose mass from orbit. Calculate changes in the planet's radiation budget. Reconstruct climates from rocks millions of years old. Send machines to Venus and read isotopes from another atmosphere. That does not make us masters of the planet. It makes us participants who can finally see part of the machinery. And once we can see it, ignorance is no longer the main constraint. Choices are... There will still be uncertainty. Climate sensitivity is expressed as a range. Regional changes remain difficult to predict precisely. Ice sheet dynamics contain unresolved questions. Cloud feedbacks continue to be studied. Future technology, population, energy systems, and politics cannot be forecast perfectly. But uncertainty does not erase direction. More carbon dioxide traps more heat. More cumulative carbon emissions produce more warming. More warming increases many risks. Reducing future emissions reduces those risks compared with continuing them. No Venus comparison is required to establish that. Venus gives us something different. Perspective. Look at Earth from space and the atmosphere seems almost non-existent. A thin blue line. The oceans appear enormous. The continents seem permanent. From that distance, climate feels like decoration painted onto a solid planet. Venus reveals the opposite truth. The atmosphere is not decoration. It can determine whether water is liquid or vapor, whether carbon sits in rock or sky, whether a surface supports oceans or crushes machinery. A relatively small portion of a planet's total mass can control the conditions experienced across its entire surface. That should permanently change how we see the air above us. And perhaps Venus once had its own version of that thin protective balance. Maybe there was a morning when clouds moved over liquid water. Maybe rain struck young volcanic rock. Maybe the planet reflected enough sunlight to remain mild while Earth was still becoming Earth. We do not know. That uncertainty is part of the beauty of the question. Future spacecraft may tell us that the vision was impossible. They may tell us that Venus was hostile almost from birth. Or they may find evidence in ancient highlands that forces us to imagine something extraordinary. Two ocean worlds once orbiting the same star. Earth and Venus. Not opposites. Sisters. Then one slowly crossed a line. The water rose into the atmosphere. Hydrogen escaped into space. The carbon cycle failed or changed beyond recognition. The old surface disappeared beneath lava and heat. And millions or billions of years later, another planet nearby developed the ability to look back and ask what happened. That is why Venus is not simply a vision of hell. It is a test of our understanding of worlds. It tells us that size alone does not make an Earth. Water alone may not make an Earth. A habitable orbit alone does not make an Earth. What matters is whether a planet can keep the relationships that allow oceans, atmosphere, rock, and energy to remain in balance through time. Venus lost that balance, or perhaps never achieved it. Earth still has it. Not perfectly, not permanently, but now. And that single word may be the most important difference between the two worlds. Because the distant future belongs to the aging sun, the ancient past belongs to geological chance, but the climate choices of the coming decades belong, at least partly, to us. Venus shows what a planet looks like when its history can no longer be undone. Earth shows something rarer, a planet whose story is still being written.